Hey everyone, and welcome back to Scientific Discovery Hub. Have you ever wondered if our corner of the universe has cosmic neighbors, or even visitors? Well, get ready to have your mind expanded. In July 2025, astronomers spotted something extraordinary, 3I Atlas, a blazing fast comet hurtling through our solar system from beyond the stars. This isn't just another icy rock, it's a galactic time capsule, carrying secrets from the Milky Way's ancient past. In this video, we'll unravel how this interstellar traveler exposed hidden mysteries about our galaxy, from its wild origins to its chemical fingerprint and the challenges of tracking it across the cosmos. So what makes 3I Atlas so special? For starters, it's one of only 3 confirmed interstellar objects ever discovered, joining the enigmatic Oumuamua and Borisov. But while those predecessors stole the spotlight, Atlas delivered a twist. It came from the southern sky, defying expectations and forcing scientists to rethink their models of interstellar traffic. We'll break down how its hyperbolic escape velocity proves it's not from here, trace its path back to the Milky Way's thick disk, a region older than our solar system, and explore its bizarre chemistry like cyanide and atomic nickel that hints at a completely different cosmic recipe. You'll also discover why spotting Atlas was like finding a needle in a stellar haystack, how it performed a daring solar dance near Mars, and what its 10-billion-year-old age reveals about the galaxy's violent youth. Plus, we'll peek into the future of interstellar exploration, including missions designed to chase down these cosmic wanderers and why studying them could answer profound questions about life's building blocks. Whether you're a space enthusiast or just curious about our place in the universe, this video will take you on a journey through science, history, and wonder. Hit play to dive into the story of 3I Atlas, a comet that reminds us we're all made of stardust, connected across time and space. Don't forget to like, subscribe, and hit that bell icon for more deep dives into the wonders of science. Let's explore the cosmos together. In the vast, silent expanse of the cosmos, where stars burn like distant beacons and galaxies spiral inches endless dance, a solitary traveler emerged from the darkness. On 1 July 2025, deep inches the arid skies of Chile's Atacama Desert, the asteroid terrestrial impact last alert system MATLAS captured a faint smudge of light moving against the backdrop of the Milky Way. At first glance, it seemed no different from countless other celestial wanderers, comets and asteroids tracing their own lonely paths through the solar system. But as the data accumulated, a startling truth revealed itself. This object, designated 3I Atlas, was not born inches the cradle of our home. It was a cosmic vagabond, a relic from another star system, flung into interstellar space eons ago, and now passing through the solar system like a ghostly whisper from the depths of the galaxy. The discovery of 3I Atlas marked a profound moment, inches humanity's quest to understand the universe. For millennia, we have gazed at the night sky, wondering whether we are alone inches the cosmos. The confirmation that interstellar objects exist, actual travelers from distant star systems, reinforces the idea that our galaxy is not a static, isolated expanse, but a dynamic, interconnected web of motion and exchange. Every interstellar visitor is a messenger, carrying clues about the birth and evolution of planetary systems, the chemistry of distant worlds, and perhaps even the raw ingredients of life itself. Yet, 3I Atlas was not merely a curiosity. Its trajectory, speed, and chemical composition offered a unique window into the processes that shape the cosmos. By studying this comet, astronomers could peer into the ancient history of the Milky Way, trace the pathways of stellar migration, and test theories about the origins of planetary systems. In the grand tapestry of the universe, 3I Atlas was both a fleeting guest and an enduring enigma, a reminder that even inches the familiar realm of our solar system, the unknown still lingers at the edges of sight. To comprehend the significance of 3I Atlas, one must first grasp the nature of interstellar objects. These are celestial bodies that originate outside the gravitational influence of our solar system, born inches the tumultuous nurseries of other stars, and later ejected into the void by the violent tides of planetary formation. Unlike asteroids and comets that orbit the Sun in predictable cycles, interstellar objects follow open-ended paths, hyperbolic trajectories that curve sharply around the Sun before escaping back into the interstellar abyss. Their defining characteristic is their hyperbolic excess velocity, the speed at which they travel beyond the Sun's gravitational pull. For 3I Atlas, this velocity was measured at 58 kilometers per second, 36 miles per second, over twice the escape velocity required to break free from the solar system entirely. Such a speed is impossible for objects native to the solar system. Comets and asteroids in our neighborhood typically move at speeds determined by their orbital mechanics around the Sun, with velocities constrained by the gravitational forces of planets and the Sun itself. However, interstellar objects arrive as cosmic projectiles, their paths shaped by the gravitational slingshots of distant stars or the explosive violence of supernovae. When 3I Atlas was discovered, its trajectory was already clear. It entered the solar system from the direction of the constellation Sagittarius, near the galactic center, and would exit toward the constellation Lyra, never to return. This one-way journey confirmed its interstellar origin beyond doubt. The detection of 3I Atlas also highlighted the limitations of our observational tools. For much of its approach, the comet remained hidden in the crowded starfields near the galactic center, a region so densely packed with stars that distinguishing a faint interloper was akin to spotting a firefly as a city's glow. It was only through the combined efforts of ground-based telescopes, including the Zwicky Transient Facility and the Hubble Space Telescope, that its true nature became evident. These instruments not only tracked its motion, but also analyzed its composition, revealing a cocktail of volatile gases, carbon dioxide, water vapor, cyanide, and atomic nickel, that hinted at its alien heritage. Unlike the comets of the solar system, which often bear the imprint of the Sun's influence over billions of years, 3I Atlas carried the unaltered fingerprint of its distant birthplace. The discovery of 3I Atlas opened a new chapter in the study of interstellar objects, but it also raised profound questions. If this comet hailed from the thick disk of the Milky Way, a region populated by some of the galaxy's oldest stars, then it could be a relic from an era predating the solar system itself. The thick disk, a sprawling layer of stars and gas above and below the galactic plane, is a graveyard of ancient stellar populations, many of which formed when the Milky Way was young and chaotic. By analyzing the comet's velocity components, astronomers deduced that 3I Atlas belonged to this population. Its high vertical velocity, 18.5 kilometers per second, indicating it had spent eons traversing the galaxy's turbulent expanse. The implications of this finding are staggering. If 3I Atlas is indeed 7 to 14 billion years old, it predates the formation of Earth by nearly 3 billion years. Such an object could serve as a time capsule, preserving the primordial conditions of the galaxy in its icy nucleus. Its composition, rich in carbon dioxide, and lacking the heavy elements abundant in younger stars, suggests it originated in a metal-poor environment, possibly a protoplanetary disk around a dying red giant, or a binary star system disrupted by gravitational chaos. These insights challenge existing models of planetary system formation, which assume that all comets and asteroids arise from the same reservoirs of material. Instead, 3I Atlas implies that interstellar objects may be as diverse as the stars themselves, each carrying the unique signature of its host system. Moreover, the comet's southern origin defied expectations. Previous studies predicted that most interstellar objects would approach the solar system from the direction of the solar apex, the point in the sky where the Sun is moving, relative to the local standard of rest. Yet 3I Atlas arrived from the opposite hemisphere, a result of its affiliation with the thick disk. This anomaly suggests that our understanding of interstellar dynamics is incomplete. Are southern origin interstellar objects rarer, or have we simply lacked the observational tools to detect them? The answer could reshape our maps of galactic traffic patterns and refine the search for future interstellar visitors. Perhaps most tantalizing is the question of what else 3I Atlas might carry. While its gases and dust offer clues to its chemical history, the comet's nucleus remains shrouded in mystery. The inability to separate its light from the coma has left its size uncertain, with estimates ranging from 320 meters to 5.6 kilometers inches diameter. Yet even a small nucleus could harbor secrets. Could it contain organic molecules, the precursors to life? Might it preserve traces of a lost civilization, or evidence of exotic planetary processes? As telescopes like the James Webb Space Telescope continue to probe its coma, each new observation brings us closer to deciphering the comet's cosmic story. To fully appreciate the journey of 3I Atlas, we must turn to the fundamental laws that govern its motion. The comet's hyperbolic trajectory is not a random accident, but a consequence of the delicate balance between gravity and velocity. When an object enters the solar system from interstellar space, its speed determines whether it will be captured into an orbit or hurled back into the void. The escape velocity, the minimum speed needed to break free from the sun's gravitational grip, is approximately 42 kilometers per second at Earth's distance from the sun. 3I Atlas exceeded this threshold by a factor of 1.4, ensuring its one-way passage. This velocity is not inherent to the comet itself, but is instead a product of its origin. Stars inches the thick disk move on inclined orbits, their motions influenced by the gravitational tides of the Milky Way's spiral arms and central bulge. Over billions of years, these motions stir up interstellar debris, scattering it like leaves inches a cosmic wind. When a star's gravitational field perturbs a planet or moon, the resulting ejection sends it careening into interstellar space, where it becomes a transient traveler. The fact that 3I Atlas retained its high velocity, despite the solar system's gravitational pull, underscores the immense energy required to launch it from its distant home. Yet even with its blistering speed, 3I Atlas will not vanish without a trace. As it approaches perihelion, the point of closest approach to the sun, it will experience a brief moment of transformation. The sun's heat will sublimate its ices, releasing plumes of gas and dust that may reveal glimpses of its internal structure. Though it will remain invisible to Earth-based observers during this phase, spacecraft orbiting Mars may catch a fleeting view of the comet's coma. A final act inches its interstellar pilgrimage. But what lies beyond this encounter? Where will 3I Atlas go next? The answer lies inches the unseen forces that shape the galaxy, a subject we will explore inches the next segment. To understand the comet's ultimate fate, we must consider not only the physics of its motion, but also the vast, unseen architecture of the Milky Way itself. In the vast tapestry of the cosmos, where stars burn like distant beacons and planets drift inches silent orbits, the arrival of a visitor from beyond the sun's dominion is an event of profound significance. Such was the case when, on 1 July 2025, the asteroid terrestrial impact last alert system Atlas, stationed at Rio Hurtado, Chile, detected a faint, fleeting speck of light hurtling through the inner solar system. What appeared as a mere point of illumination soon revealed itself to be something extraordinary. An interstellar comet, later designated 3I Atlas, CSAR 2025 N1. Unlike the countless asteroids and comets that originate within the solar system, this object did not belong to the familiar celestial neighborhood of planets and moons. Instead, it carried the unmistakable signature of an interloper, a traveler from the depths of interstellar space, bearing witness to the cosmic forces that shaped its distant home. As 3I Atlas entered the realm of the sun, it carried with it a story millions, perhaps billions of years inches the making. Its trajectory was clear evidence of an origin beyond the gravitational pull of the solar system. With a hyperbolic excess velocity of 58 kilometers per second, it moved too quickly to be captured by the sun's gravity, destined to escape back into the interstellar void after its brief encounter. This speed alone marked it as an outsider, a rare and fleeting guest inches a cosmic theater where most objects are bound to the gravitational embrace of their parent star. Yet, even inches its transient passage, 3I Atlas offered a glimpse into the mysteries of the universe beyond our own planetary backyard. The discovery of 3I Atlas followed inches the footsteps of two other interstellar interlopers, 1I Oumuamua, inches 2017, and 2I Borisov, inches 2019. Each of these objects had challenged humanity's understanding of the cosmos, revealing that the solar system is not an isolated island, inches the galaxy, but rather one among many inches a vast and interconnected web of celestial motion. While Oumuamua remained enigmatic, its nature debated between asteroid and comet, and Borisov displayed the familiar characteristics of a comet, 3I Atlas emerged with a clarity of purpose. Its activity, its coma of gas and dust, and its chemical composition painted a picture of an ancient traveler, forged inches the crucible of another star system, and now offering a rare window into the chemistry and dynamics of distant worlds. As scientists and stargazers turned their eyes toward this interstellar visitor, they were not merely observing a passing object, but participating in a moment of cosmic connection. 3I Atlas was a reminder that the universe is teeming with motion, with objects constantly transit, shaped by the gravitational tides of stars and the unseen forces that govern the cosmos. In the quiet glow of its coma and the whisper of its escape velocity, 3I Atlas carried the echoes of its birthplace, a place far removed from the warmth of the sun, yet intimately linked to the same cosmic processes that birthed the stars and planets of the Milky Way. The defining characteristic of 3I Atlas is its hyperbolic trajectory, a path that curves outward from the sun with such vigor that it will never return. This trajectory is the result of an escape velocity exceeding the gravitational binding energy of the solar system. To understand this phenomenon, one must consider the balance between kinetic energy and gravitational potential energy. For an object to escape the gravitational influence of a massive body like the sun, it must possess sufficient kinetic energy to overcome the pull of gravity. The escape velocity required to break free from the solar system at a given distance from the sun can be calculated using Newtonian mechanics, taking into account the mass of the sun and the distance from its center. At 1 astronomical unit, AU, the average distance between Earth and the sun, the escape velocity is approximately 42 kilometers per second. However, 3I Atlas was observed moving at a much greater speed, 58 kilometers per second, meaning it had more than enough kinetic energy to defy the sun's gravity and continue on its interstellar journey. This hyperbolic trajectory is not a product of internal propulsion or artificial acceleration, but rather the consequence of gravitational interactions inches its home system. Before 3I Atlas ventured into the solar system, it must have resided inches the gravitational well of another star system, where it was influenced by the movements of planets, stars, or even the tidal forces of a binary star. Over the course of eons, these forces could have nudged the comet into a path that eventually brought it into the gravitational domain of the sun. As it approached the solar system, the sun's gravity altered its trajectory slightly, but not enough to capture it into an orbit. Instead, 3I Atlas executed a flyby, slingshotting through the inner solar system, with a velocity that ensured its departure. The hyperbolic nature of 3I Atlas's path was confirmed through careful orbital calculations based on observations from multiple telescopes. By tracking the comet's position over time, astronomers were able to determine its velocity vector and the curvature of its orbit. The data revealed that 3I Atlas's trajectory was not an ellipse or a parabola, but a hyperbola, an open curve that diverges infinitely from the sun. This distinction is crucial, as it confirms that 3I Atlas is not a transient object caught inches a temporary orbit, but a true interstellar traveler. The hyperbolic excess velocity, the difference between the comet's actual speed and the escape velocity, was measured at 58 kilometers per second, a speed so great that even the gravitational pull of Jupiter or Saturn could not have imparted such a velocity to an object originating from within the solar system. The implications of this hyperbolic trajectory extend beyond mere classification. They offer insight into the conditions that allowed 3I Atlas to leave its home system. Unlike objects within the solar system, which are bound by the sun's gravity and follow elliptical or circular paths, interstellar comets must have been accelerated to such velocities by external forces. One possibility is that 3I Atlas was ejected from its native star system during a period of planetary instability. In young stellar systems, where planets are still forming and gravitational interactions are frequent, comets and asteroids can be gravitationally scattered by the influence of giant planets. If a massive planet, such as a gas giant, exerted a strong gravitational pull on 3I Atlas, it could have been flung outward at high speed, eventually escaping its home system. Another possibility is that 3I Atlas was influenced by the gravitational field of a passing star or the tidal forces of a binary star system, which could have imparted the necessary velocity to launch it into interstellar space. Regardless of the precise mechanism, the hyperbolic trajectory of 3I Atlas serves as a testament to the dynamic nature of the universe. It is a reminder that the cosmos is not a static expanse, but a realm of constant motion and transformation. The fact that 3I Atlas carries the imprint of its past, its velocity, its path, and its composition offers a rare opportunity to study the conditions of a distant star system. By analyzing the comet's properties, scientists can infer the nature of its origin, the processes that shaped it, and the environment in which it was born. The discovery of 3I Atlas was not a singular event, but a collaborative effort spanning multiple observatories, both professional and amateur. When the Atlas telescope at Rio Hurtado first detected the object, it was catalogued under the provisional designation A11 Pele 3Z, a placeholder name used to identify newly discovered minor planets and comets. The initial observations suggested an unusual trajectory, prompting the Minor Planet Center, MPC, to list the object on the Near-Earth Object Confirmation page. This page serves as a repository for newly discovered objects that require further observation to determine their potential threat to Earth or their orbital characteristics. Given the uncertainty surrounding 3I Atlas's path, the MPC took a cautious approach, ensuring that additional data would be gathered before drawing conclusions about its nature. As news of the discovery spread, astronomers from around the world turned their telescopes toward the object. Within days, follow-up observations from the Zwicky Transient Facility, ZTF, at Palomar Observatory, California, and the Very Large Telescope, VLT, Chile, provided critical insights into 3I Atlas's trajectory. These observations confirmed that the comet was not on a path that would bring it dangerously close to Earth, alleviating concerns about a potential impact. More importantly, they revealed that the object was moving at an extraordinary speed, far exceeding the typical velocities of solar system comets. This finding pointed toward an interstellar origin, a hypothesis that was soon corroborated by subsequent observations. One of the most pivotal moments in the discovery of 3I Atlas came when astronomers analyzed the object's spectrum. Spectroscopy, the technique of studying the light emitted or absorbed by an object, is a powerful tool for determining the composition of celestial bodies. Using ground-based telescopes and space-based instruments like the Hubble Space Telescope, scientists examined the light reflected by 3I Atlas and found signatures of volatile compounds typically associated with comets. These included water ice, carbon dioxide, and carbon monoxide, substances that sublimate when heated by the sun's radiation, releasing gas and dust to form the coma. The presence of these materials confirmed that 3I Atlas was indeed a comet, not an asteroid, and provided valuable clues about its internal structure. The challenge of studying 3I Atlas lay in its faintness. At an apparent magnitude of 18 at the time of discovery, it was barely detectable even by large telescopes. This faintness made it difficult to separate the light from the comet's nucleus, the solid core from the diffuse glow of the coma. Without a clear view of the nucleus, astronomers could only estimate its size, relying on models that accounted for the scattering of light by dust particles. The best estimates suggested that the nucleus was relatively small, with a diameter ranging from 0.32 to 5.6 kilometers, though the most likely value was less than 1 kilometer. This small size was consistent with the behavior of many solar system comets, which often have nuclei measuring just a few kilometers inches diameter. Despite its faintness, 3I Atlas was not invisible to all eyes. The James Webb Space Telescope, JWST, with its advanced infrared capabilities, provided a deeper look into the comet's composition. JWST's observations revealed an unusually high concentration of carbon dioxide, a compound that is less commonly found in solar system comets. This discovery hinted at differences in the chemical makeup of interstellar comets. Compared to their native counterparts, possibly due to variations inches the conditions of their formation environments. Additionally, the telescope detected traces of water vapor, carbon monoxide, and carbonyl sulfide substances that are typically released when cometary ices are heated by solar radiation. These findings painted a picture of a comet that, despite its alien origin, shared many similarities with the objects that populate the outer reaches of the solar system. Further analysis of 3I Atlas's trajectory revealed that it had passed through the inner solar system at a distance of 4.5 astronomical units from the Sun, placing it well beyond the orbit of Mars. As it continued its journey inward, the comet began to brighten, its coma expanding as the Sun's heat intensified. By early August 2025, 3I Atlas had crossed into the orbital zone of the asteroid belt, a region where many solar system comets originate. Yet, unlike these native comets, 3I Atlas was not bound to the Sun's gravity. Its path was clearly hyperbolic, indicating that it would soon begin its return to interstellar space. The final weeks of 3I Atlas's journey brought it closer to the Sun, where the increased solar radiation triggered a surge inches activity. Jets of gas and dust streamed from the nucleus, forming a tail that stretched across the sky. Observers equipped with large aperture telescopes were able to capture these changes inches real time, documenting the evolution of the comet as it approached perihelion, the point inches its orbit where it would be closest to the Sun. At its peak brightness, 3I Atlas reached an apparent magnitude of 11.7, making it a target for dedicated observers who sought to study its behavior before it faded once more into the darkness of space. While 3I Atlas's visibility from Earth was limited, its journey was not without significance. The comet's closest approach to the Sun occurred on 29 October 2025, at a distance of 1.36 astronomical units. From that vantage point, the Hubble Space Telescope and other instruments tracked the comet's activity, providing a wealth of data on its composition and behavior. Meanwhile, spacecraft orbiting Mars, such as NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express, were tasked with observing 3I Atlas as it passed near the red planet. These observations offered a unique perspective, allowing scientists to compare the comet's appearance from different vantage points inches the solar system. As 3I Atlas completed its brief visit to the inner solar system, it left behind a trail of unanswered questions. What was the nature of its home system? How did it acquire its hyperbolic trajectory? And what secrets did its chemical composition hold about the conditions of its birthplace? These questions, though difficult to answer, were not insurmountable. The data gathered during 3I Atlas's passage would serve as a foundation for future studies, guiding the search for other interstellar visitors and deepening humanity's understanding of the cosmos. The journey of 3I Atlas through the solar system was a fleeting one, but its implications extended far beyond the months it spent inches the Sun's domain. As scientists analyzed the comet's trajectory, composition, and behavior, they uncovered clues that pointed to an origin far removed from the familiar architecture of the solar system. The comet's hyperbolic path, its velocity, and its chemical makeup all hinted at a birthplace inches the distant past, a place where the conditions of star formation and planetary evolution differed from those inches, the Milky Way's present-day neighborhoods. Yet, to fully grasp the significance of 3I Atlas's origin, one must look beyond its immediate journey and trace its path through the vast expanse of interstellar space. The key to understanding where 3I Atlas came from lies in the analysis of its velocity vectors and the gravitational influences that shaped its trajectory. By breaking down the comet's motion into its three-dimensional components, astronomers could reconstruct the path it had taken through the galaxy. This process involved mapping the comet's position and velocity relative to the Sun, and then extrapolating its motion backward inches time. The results of this analysis revealed a startling truth. 3I Atlas had not originated from the direction of the solar apex, the region of the sky toward which the Sun is moving inches the Milky Way, but from the opposite direction, inches the southern celestial hemisphere. This finding defied initial expectations, as previous models of interstellar object trajectories had suggested that most such visitors would arrive from the solar apex. where the density of stars and the likelihood of gravitational interactions are higher. Instead, 3I Atlas's origin pointed to a region of the galaxy that was less explored and less understood, a direction where the distribution of stars and the dynamics of stellar motion had not yet been fully characterized. This southern origin raised intriguing questions about the nature of interstellar comets and the mechanisms that propelled them into the solar system. Were southern origin comets a rare anomaly, or did they represent a larger, previously undetected population of interstellar travelers? The answer to this question would require further observations and statistical analyses of future interstellar objects. However, the discovery of 3I Atlas already suggested that the solar system's encounters with interstellar visitors were more diverse than previously assumed. The comet's trajectory indicated that it had not simply drifted into the solar system by chance, but had followed a path shaped by the gravitational currents of the Milky Way. These currents, driven by the motions of stars and the unseen forces of dark matter, could have guided 3I Atlas along a route that intersected with the Sun's gravitational domain. The next step in unraveling the mystery of 3I Atlas's origin was to determine the specific region of the galaxy from which it hailed. By tracing the comet's path backward in time, astronomers identified its point of entry into the solar system as a location near the constellation Sagittarius, close to the galactic center. This region is a dense and dynamic area of the Milky Way, where the gravitational forces of the central supermassive black hole and the surrounding stars create a complex web of motion. However, the fact that 3I Atlas had not originated from the immediate vicinity of the galactic center suggested that its birthplace was located farther out. The galactic thick disk, a region characterized by older stars and a lower concentration of interstellar material. The thick disk, unlike the younger, more metal-rich thin disk where the Sun resides, is a relic of the galaxy's early formation, containing stars that formed billions of years ago. The presence of 3I Atlas this region implied that it was not a recent ejection from a nearby star system, but a remnant of an ancient era, when the conditions of the galaxy were vastly different. The age of 3I Atlas added another layer of complexity to its origin story. Studies conducted the summer of 2025 estimated that the comet was between 7.6 and 14 billion years old, making it potentially older than the solar system itself. This staggering age meant that 3I Atlas had witnessed the formation of stars and planets, a galactic environment that no longer exists. Its journey through the Milky Way had spanned epochs of cosmic change, from the violent collisions of protostars to the quiet expansion of stellar nurseries. The fact that 3I Atlas had survived for so long was a testament to the resilience of cometary bodies, which can endure the harsh conditions of interstellar space as long as they remain shielded from the destructive forces of radiation and gravitational disruption. As the data on 3I Atlas continued to accumulate, a clearer picture of its origin and history began to emerge. The comet was not merely a random wanderer, but a messenger from a distant past, carrying the imprint of its birthplace, its chemical composition and trajectory. Its journey through the solar system was a fleeting encounter, a brief exchange of information between two distinct cosmic realms. Yet, even its brief passage, 3I Atlas had provided invaluable insights into the nature of interstellar comets and the processes that shape their paths. The questions it raised about the frequency of such objects, the conditions of their formation, and the mechanisms that propel them into interstellar space would drive future research and exploration. In the coming years, as new technologies and observational techniques push the boundaries of astronomy, the study of interstellar comets would become a central focus of astrophysical research. The lessons learned from 3I Atlas would inform the search for other interstellar visitors, helping scientists to distinguish between native solar system objects and those that had originated elsewhere in the galaxy. The quest to understand the origins of 3I Atlas was not merely an academic pursuit, it was a step toward unraveling the broader narrative of the universe. A narrative which every object, every star, and every galaxy played a role, shaping the cosmic web. In the vast expanse of the cosmos, where time stretches beyond human comprehension and light becomes the only measure of distance. 3i Atlas drifts like a silent messenger from the galaxy's ancient past. Its journey began not inches the familiar cradle of the solar system, but inches the distant reaches of the Milky Way's thick disk. A region shrouded inches the quiet hum of stellar antiquity. To trace its path is to follow a thread woven through the fabric of the galaxy itself, a thread that links the present to epochs when stars were young and the cosmos was a cauldron of creation. This comet, with its hyperbolic trajectory and blistering speed, is more than a visitor. It is a relic of the Milky Way's formative years, a wanderer that has traveled for billions of years to arrive here. Now, inches our fleeting moment of observation. The discovery of 3i Atlas inches 2025 marked a turning point in humanity's quest to map the interstellar highways of the universe. Unlike the first two interstellar interlopers, Oumuamua and Borisov, this comet emerged not from the galactic halo or the solar apex, but from the southern celestial hemisphere, a direction long thought to be a blind spot for such discoveries. Its origin, pinned to the constellation Sagittarius near the Milky Way's center, evokes images of a cosmic crucible, where gravity and time conspired to forge a body that would one day cross paths with our own. Yet this is not merely a tale of a single comet's voyage. It is a story of the galaxy's layered history, of how stars and their accompanying debris have moved, collided, and scattered over eons. As we unravel the secrets of 3i Atlas's galactic roadmap, we are not just deciphering the path of a comet, we are reading the story of the Milky Way itself. To understand where 3i Atlas came from, we must first grasp the architecture of the Milky Way. Our galaxy is not a uniform expanse, but a layered tapestry of stellar populations, each with its own history and motion. The thin disk, where our sun resides, is a relatively young region, home to stars formed inches the last few billion years. Above and below it lies the thick disk, a puffed-up structure containing stars that are, on average, 10 billion years old, nearly twice the age of the solar system. These stars move inches orbits tilted relative to the thin disk, their trajectories shaped by the gravitational tides of the galaxy's violent past. Beyond them, the galactic halo encircles the Milky Way like a ghostly crown, hosting ancient globular clusters and remnants of dwarf galaxies consumed by time. 3i Atlas's origin lies inches the thick disk, a conclusion drawn from its velocity components and orbital dynamics. When the comet entered the solar system, it carried with it a signature of motion, a radial velocity of motion 51.0 kilometers per second, U component, and a vertical velocity of puns 18.5 kilometers per second, Watts component, relative to the Sun. These numbers, though seemingly abstract, are keys to unlocking the comet's galactic provenance. The negative U velocity indicates that the comet was moving away from the galactic center at the time of its arrival, while the positive Watts velocity suggests it was ascending above the galactic plane. Together, these velocities paint a picture of a body that has spent most of its existence inches the thick disk, where stars exhibit similar kinematics. The thick disk is not a static region. It is a dynamic reservoir of stellar motion, shaped by the gravitational interplay of the galaxy's spiral arms, dark matter, and mergers with smaller satellite systems. Stars born inches the thick disk tend to have lower metallicities. Their compositions lack the abundance of heavy elements found inches younger stars like the Sun. This is because the thick disk stars formed earlier, when the galaxy had not yet cycled enough gas through supernovae and stellar winds to enrich it with heavier elements. For 3i Atlas to originate from this population, it must have been ejected from a planetary system that existed inches an era when the Milky Way was still assembling itself. The study of 3i Atlas's trajectory also reveals another crucial detail. Its path through the solar system was not random. While Oumuamua and Borisov appeared to hail from the galactic halo and the solar apex respectively, 3i Atlas's origin inches the thick disk suggests that interstellar objects may not be uniformly distributed across the galaxy. Instead, they may reflect the density and motion of their parent stellar populations. This realization challenges earlier assumptions that interstellar visitors would predominantly come from the direction of the solar apex, the point toward which the Sun is moving relative to nearby stars. The fact that 3i Atlas emerged from the southern hemisphere a region less scrutinized by ground-based telescopes due to atmospheric distortions, hints that our observational biases may have obscured many such ancient travelers. The implications of 3I Atlas's origin extend far beyond its immediate trajectory. This comet is a fossil of the Milky Way's infancy, a fragment of a planetary system that predates the birth of our own solar system by billions of years. Its existence forces us to reconsider the timescales of galactic evolution and the mechanisms by which interstellar objects are ejected from their native systems. In the thick disk, where stars are older and their orbits more chaotic, the likelihood of gravitational interactions that could dislodge comets or asteroids from their host systems is higher. Such ejections might occur when binary stars or passing rogue planets perturb the delicate balance of a planetary system, sending fragments hurtling into the void. Over eons, these objects drift through the galaxy, their paths dictated by the gravitational pull of unseen masses and the slow churn of the galactic tide. The age of 3I Atlas, estimated between 7.6 and 14 billion years, places it in a unique position to inform our understanding of the Milky Way's early history. If the thick disk indeed harbors comets that are relics of the galaxy's formative era, then studying their compositions could provide insights into the primordial materials available during the first billion years of the galaxy's life. This, in turn, could shed light on the conditions under which the first generations of stars and planets formed. For example, the presence of carbon dioxide and cyanide in 3I Atlas's coma suggests that its parent system may have had a chemistry distinct from that of the solar nebula, where water and ammonia dominate. Such differences could arise from variations in temperature, pressure, or the availability of raw materials in the protoplanetary disks of distant stars. Moreover, 3I Atlas's journey raises profound questions about the long-term fate of interstellar objects. If the thick disk is a prolific source of such wanderers, how do they survive the hazards of the galactic environment? The Milky Way is not empty space. It is a web of gravitational influences, from the magnetic fields of giant molecular clouds to the tidal forces of the galactic core. Yet 3I Atlas has endured for billions of years, navigating these perils to eventually intersect with the solar system. Its survival suggests that interstellar objects may be more resilient than previously thought, capable of preserving their primordial signatures despite the turbulent conditions of the interstellar medium. Perhaps the most tantalizing implication of 3I Atlas's origin is its potential role in the broader context of galactic archaeology. By mapping the trajectories of interstellar comets, astronomers may one day reconstruct the migration patterns of stars and their accompanying debris, just as fossils on Earth allow paleontologists to piece together the history of life. Interstellar objects like 3I Atlas could serve as cosmic fossils, offering glimpses into the movements of entire stellar systems. Future surveys, equipped with advanced telescopes and machine learning algorithms, may uncover a wealth of such objects, each carrying a unique story of its birthplace and journey. Together they could chart the Milky Way's evolution, revealing how stars, planets, and even life itself have been shaped by the galaxy's dynamic past. Yet, the true significance of 3I Atlas lies not only in its galactic pedigree, but in the secrets it carries within its icy heart. While its trajectory tells a story of ancient migrations, its composition offers a window into the chemistry of a forgotten epoch. The gases and ices that escape from its nucleus as it warms in the sun's embrace are more than ephemeral wisps. They are the fingerprints of a planetary system that no longer exists, preserved for eons in the deep freeze of interstellar space. To decode these chemical signatures is to read the recipe of a world born in the Milky Way's youth, a world that may have once harbored the building blocks of life, or perhaps something even stranger. As 3I Atlas continues its brief, blazing arc through the inner solar system, it invites us to consider the profound interconnectedness of the cosmos. The same processes that forge stars and planets in distant corners of the galaxy have also sculpted the materials that now drift silently through space. In the next segment, we will delve into the comet's chemical composition, exploring how its peculiar mix of carbon dioxide, cyanide, and other compounds may offer clues to the conditions of its birthplace, what it might mean for the search for life beyond Earth. For inches, the silent whispers of a wandering comet, we may yet find echoes of the universe's earliest days waiting to be heard. Amid the vast expanse of the cosmos, where stars are born and die inches, an eternal cycle of creation and destruction, a silent traveler drifts through the void. 3i Atlas, the third confirmed interstellar visitor to our solar system, carries with it a secret, a glimpse into the primordial chemistry of a distant star system. Unlike the familiar icy bodies that populate the outer reaches of our own planetary neighborhood, this comet is a cosmic cocktail, its composition a testament to the diverse and enigmatic processes that shape worlds across the galaxy. As it hurtles through the inner solar system, its nucleus releases a complex mixture of gases, each molecule whispering tales of its ancient origins. Spectroscopic analyses conducted by the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, have revealed an astonishing array of volatile compounds within 3i Atlas's coma. Carbon dioxide dominates its outgassing, far exceeding the proportions typically observed in comets native to our solar system. Alongside this, traces of water vapor, carbon monoxide, and carbonyl sulfide emerge, their delicate balance hinting at a formation environment unlike any we have encountered before. Yet it is the presence of cyanide and atomic nickel that truly sets this comet apart. These elements, rare inches, the icy remnants of our own solar system's early history, suggest a chemical recipe forged inches the cold, distant reaches of another stellar nursery. What makes 3i Atlas so remarkable is not merely the abundance of these compounds, but the way they coalesce into a singular, coherent profile. Each molecule is a piece of a puzzle, one that scientists are only beginning to assemble. The comet's coma, illuminated by the sun's radiant energy, becomes a fleeting laboratory where ancient chemistry unfolds inches real time. As the nucleus warms, volatile ices sublimate into gas, carrying with them the echoes of a bygone era. In this fragile, ephemeral cloud, the ingredients of life itself may once have taken shape. Carbon-based molecules, the building blocks of organic complexity, suspended inches, a frozen relic of the cosmos. The implications of this discovery are profound. 3i Atlas is not just a wandering object from the depths of interstellar space. It is a chemical fossil, a relic of a time when the Milky Way was still young and planetary systems were inches their infancy. Its journey through our solar system is more than a mere celestial encounter. It is a message from the past, a glimpse into the conditions that gave rise to worlds beyond our own. And as we study its spectral signature, we begin to understand that the universe is not a uniform expanse, but a tapestry of chemical diversity, where each star system tells its own unique story. As 3i Atlas continues its brief passage through the inner solar system, the sun's rays serve as both a catalyst and a revealer, unlocking the secrets hidden within its icy nucleus. The process begins with sublimation, the transformation of solid ice directly into gas, as the comet's surface is warmed by the sun's energy. This heating causes the frozen reservoirs of carbon dioxide, water ice, and other volatiles to erupt into the coma, a tenuous envelope of gas and fine dust that envelops the nucleus. The James Webb Space Telescope, with its unparalleled sensitivity to infrared wavelengths, has captured these emissions inches exquisite detail, revealing the precise chemical fingerprints of the comet's volatile inventory. Among the most striking revelations is the dominance of carbon dioxide. In contrast to the comets of our solar system, where water ice typically constitutes the largest fraction of a comet's volatile content, 3i Atlas exhibits an unusually high concentration of CO2. This suggests that its formation environment was significantly colder than the Kuiper belt, the region of our solar system where most comets originate. In such frigid conditions, carbon dioxide would freeze out at greater distances from its parent star, embedding itself deep within the comet's icy matrix. The presence of water ice and vapor, though present, exists inches relatively modest quantities compared to CO2, reinforcing the notion that 3i Atlas formed inches a region where temperatures were too low to allow water to condense inches significant amounts. Yet the comet's chemical profile extends beyond the familiar. Traces of carbon monoxide and carbonyl sulfide further complicate the picture, indicating a complex interplay of molecular synthesis and preservation over eons. These compounds are typically associated with the coldest regions of molecular clouds, where chemical reactions proceed slowly, allowing exotic molecules to form and remain trapped inches ice. The presence of cyanide, specifically hydrogen cyanide, is particularly intriguing. Cyanide is a key precursor to amino acids, the fundamental building blocks of proteins, and its detection inches 3I Atlas raises tantalizing questions about the universality of prebiotic chemistry. While the comet itself is unlikely to host life, the presence of such compounds suggests that the ingredients necessary for life may be widespread throughout the cosmos. Perhaps the most surprising discovery comes from the detection of atomic nickel vapor inches, the comet's coma. This element, typically locked within rocky planetary bodies, is rarely found inches the gaseous state within comets. Its presence inches 3I Atlas implies that the comet's formation environment contained a unique combination of temperature and pressure that allowed metallic elements to become incorporated into its icy structure. This finding challenges existing models of comet formation, which often assume that such volatile rich bodies arise from purely icy, low metallicity regions of their parent star systems. Instead, 3I Atlas hints at a more dynamic and chemically diverse process. 1 inches which metal-rich materials may have played a role, inches shaping the comet's composition. Taken together, these observations paint a vivid picture of a celestial body that is both alien and intimately connected to the broader cosmic narrative. 3I Atlas is not merely a drifting fragment of interstellar debris. It is a record of the conditions that existed inches its place of origin, billions of years ago. Its chemical makeup offers a rare opportunity to study the diversity of planetary systems beyond our own, revealing that the universe is not a monochrome expanse, but a kaleidoscope of chemical richness. As scientists continue to analyze its spectral signatures, they are piecing together a deeper understanding of how planetary systems form, evolve, and exchange material across the vast distances of interstellar space. The discovery of 3I Atlas forces a reconsideration of long-held assumptions about the homogeneity of comets and the universality of their formation processes. For decades, astronomers have studied comets from our solar system, interpreting them as relics of the early protoplanetary disk that gave rise to the planets. These icy bodies, believed to have formed inches the cold outer reaches of the solar system, share common chemical signatures primarily dominated by water ice, methane, ammonia, and carbon monoxide. Their similarities have led to the assumption that all comets, regardless of their origin, follow a similar evolutionary path. However, 3I Atlas defies this expectation. Its chemical profile is markedly different, suggesting that the processes governing its formation were shaped by a unique set of environmental conditions, one that diverges from the blueprint of our own solar system. This divergence raises a compelling question. If comets are not universally alike, then how many different types of planetary systems exist across the galaxy? The presence of carbon dioxide as the dominant volatile inches, 3I Atlas, implies that its parent star system formed inches a colder region than the Kuiper Belt, where water ice was less abundant. Such conditions may be more common inches, certain parts of the galaxy, where the density of interstellar material and the distribution of heavy elements vary. The detection of cyanide and atomic nickel further complicates the picture, suggesting that the comet's formation environment was not only cold but also chemically rich, containing a mix of volatile ices and metal-rich materials. These findings indicate that the processes of planet formation are not uniform across the cosmos, but rather shaped by the specific conditions of each star-forming region. Moreover, the chemical diversity of 3I Atlas challenges the notion that all comets originate from the same kind of reservoir within their respective planetary systems. In our solar system, comets are typically divided into 2 main categories: Jupiter family comets, which originate from the Kuiper Belt and have relatively short orbital periods, and long-period comets, which hail from the more distant Oort cloud. Both groups exhibit broadly similar compositions, reinforcing the idea that they formed under comparable conditions. However, 3I Atlas does not fit neatly into either category. Its extreme hyperbolic trajectory and high velocity clearly mark it as an interstellar object. but its chemical composition suggests that it may belong to a completely different class of comets, one that has no direct counterpart within our own planetary system. This discovery opens the door to the possibility that other interstellar comets may exhibit even greater variability, each carrying the unique imprint of its birthplace. Inches the Milky Way. Beyond the realm of planetary science, the chemical richness of 3I Atlas has profound implications for the search for extraterrestrial life. The presence of cyanide and other carbon-based molecules inches its coma suggests that the building blocks of life may be more widespread inches the universe than previously thought. While the comet itself is not a habitable world, its composition hints at the possibility that other planetary systems may harbor environments conducive to the emergence of life. The fact that such organic molecules can be preserved inches the icy mantles of comets over billions of years, implies that the ingredients necessary for life may be transported across interstellar space, carried by these cosmic messengers from one star system to another. In this sense, 3I Atlas is not just a relic of the past, it is a harbinger of the future, a reminder that the seeds of life may be sown far and wide across the cosmos. As scientists continue to unravel the mysteries of 3I Atlas, they are left with a tantalizing question. How many other interstellar comets like this one have passed through our solar system unnoticed? The detection of 3I Atlas represents a milestone inches our understanding of the universe. But it is only the beginning. With improved observational technologies and more sensitive surveys, future discoveries may reveal an even greater diversity of interstellar objects, each offering a new perspective on the vast and intricate web of cosmic evolution. In the grand tapestry of the universe, 3I Atlas is but a single thread, yet it serves as a powerful reminder that the cosmos is not a uniform expanse, but a dynamic and ever-changing realm of infinite possibilities. Despite its scientific significance, 3I Atlas remained elusive for much of its journey through the inner solar system. Its intrinsic faintness, combined with its position against the dense star fields near the galactic center, rendered it nearly invisible to observers for weeks. Only through the relentless efforts of automated sky surveys and the keen eyes of dedicated astronomers was this interstellar traveler finally brought into focus. The challenge of detecting such a dim object against the backdrop of countless stars underscores the difficulty of uncovering the hidden messages that pass through our cosmic neighborhood. At its brightest, 3I Atlas shone with an apparent magnitude of just 11.5, an object too dim to be seen with the naked eye, or even through a standard pair of binoculars. This level of faintness required specialized equipment, telescopes equipped with sensitive detectors, and large apertures capable of gathering the faint light reflected from the comet's coma. Even then, the comet remained a ghostly presence, barely distinguishable from the myriad of stars that crowded its path. From July to September 2025, 3I Atlas traced a slow arc across the constellations of Sagittarius, Ophiuchus, Scorpius, and Libra. In the early stages of its apparition, it lingered inches the rich star fields of Sagittarius, where the density of stars posed a formidable obstacle. Observers had to sift through vast numbers of celestial objects to identify the faint diffuse glow of the comet, which often appeared as little more than a smudge against the stellar backdrop. The situation grew even more challenging as 3I Atlas approached perihelion inches. By this point, its solar elongation, the angle between the comet and the sun, as viewed from Earth, had diminished to less than 30 degrees, placing it perilously close to the sun inches the sky. This meant that the comet became visible only briefly after sunset, when the sky was still illuminated by the sun's residual glow. Observers inches temperate latitudes found themselves at a disadvantage, as the comet's proximity to the horizon limited their ability to track its movement. Only those inches equatorial regions had a fleeting window to observe the comet before it disappeared behind the sun, entering solar conjunction and vanishing from view for a time. The difficulty of observing 3I Atlas highlights the limitations of current astronomical technology. Inches detecting interstellar objects. While the comet was eventually spotted by the asteroid terrestrial impact last alert system Atlas, survey Inches Chile, its initial discovery was delayed due to the sheer density of stars inches its path. The galactic center, a region teeming with millions of stars, presented a near impenetrable barrier for automated detection algorithms. which struggled to distinguish the faint, moving object from the static sea of background stars. It was only through follow-up observations from other observatories, including the Zwicky Transient Facility and contributions from amateur astronomers, that 3I Atlas's true nature was revealed. This experience serves as a sobering reminder of how much remains hidden in the cosmos. The vast majority of interstellar objects that pass through the solar system may go undetected, slipping through the gaps inches our observational capabilities, like whispers lost inches the wind. Yet with the continued development of next-generation telescopes and more sophisticated detection algorithms, the likelihood of discovering these cosmic travelers increases. Future missions, such as the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to revolutionize our ability to detect faint, fast-moving objects in the night sky. With enhanced sensitivity and broader coverage, such projects may uncover a wealth of interstellar visitors, each carrying their own unique stories from the farthest reaches of the galaxy. As 3I Atlas faded from view in the late months of 2025, its legacy endured in the data it left behind. The challenge of tracking this elusive comet was a testament to the perseverance of those who seek to understand the universe. It also served as a humbling reminder of how much we still have to learn. The cosmos is vast, its inhabitants numerous and varied, and the faintest glimmer in the night sky may hold the key to unlocking the greatest mysteries of existence. In the vast, silent expanse of the cosmos, where time stretches into eons and distances defy comprehension, the universe reveals itself in fragments. Among these fragments, 3I Atlas stands as a fleeting whisper, a comet born not in our solar system, but among the distant ancient stars of the Milky Way, discovered in the summer of 2025. This interstellar visitor is a relic from a time before our sun ignited, carrying secrets of stellar nurseries and the chaotic dance of planetary systems. To find 3I Atlas was to glimpse a needle in a cosmic haystack, a faint icy body hurtling through the heavens at over 58 kilometers per second, its path etched against the backdrop of the galactic center's dazzling starfields, yet like a firefly flickering in a storm of fireworks. Its presence was nearly lost to the noise of the cosmos. How did astronomers armed with telescopes and algorithms pierce the veil of obscurity to uncover this enigmatic traveler? The answer lies not just in the tools of modern astronomy, but in the collaborative spirit of a global community united by curiosity. The story of 3I Atlas is one of serendipity and precision. It begins in the arid skies of northern Chile, where the Atlas Observatory scans the heavens for threats to Earth. Yet, on 1 July 2025, its sensors captured something far stranger, a point of light moving at an impossible speed, its trajectory defying the gravitational embrace of the solar system. This object, later named 3I Atlas, was not bound to the sun's influence. Instead, it was a wanderer from the depths of interstellar space, a testament to the dynamic, interconnected nature of galaxies. But its discovery was no simple feat. The comet's faintness, peaking at a mere 11/5 magnitude, and its position near the Milky Way's dense core posed challenges akin to spotting a snowflake in a hurricane. Only through the combined efforts of professional observatories, amateur astronomers, and cutting-edge technology did 3I Atlas emerge from the shadows. Its journey into our system is a reminder that the universe is not a static void, but a living, breathing tapestry of motion and mystery. To comprehend the difficulty of detecting 3I Atlas, one must imagine the night sky as a vast, shifting ocean. In this ocean, the Milky Way's galactic center is a turbulent whirlpool, teeming with stars, nebulae, and the faint glow of interstellar dust. Here, the density of celestial objects is so great that distinguishing individual points of light becomes a Sisyphean task. 3I Atlas entered this chaos on a diagonal path, its position near the galactic plane making it nearly indistinguishable from the countless background stars. Its faint magnitude, equivalent to a pinprick of light, barely perceptible even to large telescopes, compounded the challenge. For context, the human eye can see objects as faint as magnitude 6 under ideal conditions, while the most powerful ground-based telescopes can detect objects as faint as magnitude 25. 3I Atlas at its brightest hovered around magnitude 11.5, a ghostly shimmer hidden inches plain sight. The breakthrough came not from a single instrument, but from a symphony of technologies working inches concert. The Atlas system, designed to detect near-Earth asteroids, first flagged the anomaly on 1 July 2025. Its automated software, trained to track moving objects, identified the comet's rapid motion against the fixed stars. However, the initial data was inconclusive. Was this a comet, an asteroid, or something else entirely? The object's trajectory suggested an interstellar origin, but confirmation required more precise measurements. Enter the Zwicky Transient Facility, ZTF, a survey telescope, Inches, California, capable of scanning the entire northern sky every few nights. Within hours of Atlas's discovery, ZTF's wide-field camera captured pre-discovery images, dating back to early June 2025, revealing the comet's path in exquisite detail. These observations, combined with follow-up data from the Canada-France-Hawaii telescope and the Lowell Discovery Telescope, painted a picture of a body traveling at hypervelocity, over 61 kilometers per second, relative to the Sun. Yet the true marvel lay in the human element. While professional observatories provided the raw data, it was the vigilance of amateur astronomers like Sam Dean that uncovered critical clues. Dean noted that Atlas's earlier images from late May 2025 showed the same object, but its faintness and position near the galactic core had masked its presence. The galactic center, a region of intense stellar activity, is a double-edged sword. It offers a wealth of scientific targets, but drowns out subtle signals like those from 3I Atlas. Here, the comet's journey became a game of patience and persistence. Algorithms designed to sift through millions of data points were tuned to recognize patterns invisible to the naked eye. Machine learning models, trained on decades of astronomical data, flagged anomalies that hinted at interstellar motion. The result was a collaborative triumph, proof that the boundaries between professional and amateur astronomy are increasingly blurred in the digital age. By mid-July 2025, the evidence was irrefutable. 3I Atlas was not merely an interstellar object, it was a comet. Observations revealed a faint coma and a tenuous tail, confirming the presence of volatile ices beneath its surface. The International Astronomical Union's Minor Planet Center, MPC, officially classified it as 3I Atlas, the third confirmed interstellar interloper after Oumuamua and 2I Borisov. Yet the story was far from complete. As scientists analyzed its trajectory, they realized that 3I Atlas was destined to approach the Sun at a distance of 1.36 AU, closer than Mars but far enough to avoid disintegration. Its path was a hyperbolic arc, a cosmic slingshot that would carry it back into the interstellar void within months. But what of its origins? Where had this ancient wanderer come from, and what secrets did it hold? The discovery of 3I Atlas is more than a milestone in planetary science. It is a portal to the ancient history of the Milky Way. By tracing its trajectory backward time, astronomers determined that the comet originated from the thick disk of our galaxy, a region inhabited by some of the oldest stars. Unlike the thin disk where the Sun resides, the thick disk is a relic of the Milky Way's early formation, containing stars with lower metallicities and longer orbital periods. The fact that 3I Atlas hails from this region suggests it predates the solar system by billions of years. Studies led by Matthew Hopkins and his team in July 2025 estimated its age to be between 7.6 and 14 billion years, placing it in the twilight of the universe's youth. This makes 3I Atlas not just an interstellar traveler but a time capsule, preserving material from an era when the galaxy was still coalescing. What makes 3I Atlas particularly intriguing is its composition. Spectroscopic analyses by the James Webb Space Telescope revealed an unusual richness in carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These volatile compounds are typically associated with comets in the outer solar system, where temperatures are low enough to preserve ices. Yet 3I Atlas's chemical profile hints at a different origin story. Its high concentration of CO2 suggests it formed in a cold, distant environment. Perhaps in the protoplanetary disks of a long-dead star, or in the frigid outskirts of a neighboring planetary system. Furthermore, the detection of cyanide gas and atomic nickel vapor, observed by the Very Large Telescope, mirrors the chemistry of solar system comets, but with subtle variations. These differences offer clues about the conditions inches the comet's home system, potentially shedding light on the diversity of planetary formation processes across the galaxy. But perhaps the most profound implication of 3I Atlas lies inches its hyperbolic trajectory. With a heliocentric velocity of 58 kilometers per second, it is moving too fast to be gravitationally captured by the Sun. Its path is unbound, a cosmic express train hurtling toward the stars. This raises a tantalizing question. If 3I Atlas is older than the solar system, what forces propelled it on this journey? One possibility is that it was ejected from its native system during a violent gravitational interaction, perhaps a close encounter with a giant planet or a binary star. Such ejections are common in young stellar clusters, where the gravitational tides of multiple stars can destabilize planetary orbits. If 3I Atlas indeed formed such a cluster, its survival over billions of years speaks to the resilience of cometary bodies. It also implies that interstellar comets may be more common than previously thought, drifting silently through the galaxy like forgotten echoes of stellar births and deaths. Yet the challenges of detecting 3I Atlas underscore the limitations of our current technology. Despite the comet's brief visit to the inner solar system, its faintness and position near the galactic center meant it remained invisible to all but the most sensitive instruments. This raises an unsettling question. How many other interstellar visitors have we missed? With only 3 confirmed interstellar objects to date, our understanding of this phenomenon remains fragmented. Future surveys, such as those conducted by the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to change this. By scanning the entire southern sky every few nights, LSST will detect fainter objects and trace their trajectories with unprecedented precision. Paired with machine learning algorithms capable of identifying subtle anomalies, such surveys could uncover a flood of interstellar comets and asteroids, transforming our view of the Milky Way into a bustling highway of cosmic traffic. Moreover, 3I Atlas's discovery highlights the power of collaboration in modern astronomy, from the automated pipelines of Atlas and ZTF to the keen eyes of amateur astronomers. Its detection was a collective effort. In an era where data volumes outpace human capacity for analysis, citizen science initiatives and open access databases have become indispensable. Projects like the Global Sky Partnerships and the Zooniverse platform enable volunteers worldwide to contribute to scientific discovery, democratizing the process of exploration. As 3I Atlas recedes into the void, it leaves behind a legacy not just of knowledge but of unity, a reminder that the quest to understand the cosmos is a shared endeavor. With its origins unraveled and its identity affirmed, 3I Atlas turned its gaze toward the heart of the solar system. By October 2025, it would reach perihelion, the closest point inches its trajectory to the Sun, at a distance of 1.36 AU, nestled between the orbits of Earth and Mars. Though this might seem perilously close, the comet's path ensured it would not pose a threat to our planet. Yet the Sun's influence loomed large, its searing heat set to transform 3I Atlas ways both beautiful and destructive. The sublimation of its ices, the expulsion of gas and dust, and the sculpting of its coma and tail would create a fleeting spectacle, a final act of cosmic theater before the comet resumed its journey into interstellar exile. But what exactly would happen as 3I Atlas danced with the Sun? And what secrets might this encounter reveal about the comet's composition and history? The answers lie in the crucible of solar radiation, where the fragile balance between preservation and destruction determines the fate of interstellar wanderers. In the vast silent expanse of the cosmos, where time stretches into epochs beyond human comprehension, a traveler from another star system has arrived. 3I Atlas, an interstellar comet, glides through the inner solar system like a ghostly emissary from the distant past. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, Chile, this object is not bound to the Sun's gravitational embrace. Instead, it moves on a hyperbolic trajectory, a cosmic slingshot that will carry it back into the interstellar void within months. Its journey is brief by cosmic standards, yet profound in its implications. 3i Atlas is the third such visitor ever identified, following the enigmatic 1i Oumuamua and 2i Borisov, and it carries secrets that could redefine our understanding of planetary formation, stellar evolution, and the shared history of stars across galaxies. As it approaches its closest point to the Sun on 29 October 2025, scientists and stargazers alike turn their eyes skyward, not merely to witness a fleeting spectacle, but to decode the story etched into its icy heart. The arrival of 3i Atlas is more than an astronomical event. It is a reminder of humanity's place, inches the grand tapestry of the universe. We are but observers on a tiny blue planet, gazing up at a sky that has always held visitors from afar. Yet now, with advanced telescopes and global networks of observatories, we can trace the paths of these interstellar wanderers with unprecedented precision. 3i Atlas, though faint and distant, is a beacon of curiosity, a challenge to our assumptions about the origins of comets and the interconnectedness of stellar systems. What can this ancient comet tell us about the birthplaces of stars, the chemistry of distant worlds, and the forces that shape the cosmos? Its answer lies in the dance it performs with the sun, the subtle glow of its coma, and the whispers of its volatile composition. At its core, 3i Atlas is a relic of stellar nurseries long since faded into memory. Its nucleus, a frozen mixture of ice, rock, and organic compounds, is encased in a tenuous coma, a halo of gas and dust, released as the comet warms under the sun's rays. This transformation is a ballet of sublimation and solar radiation, a process that has shaped comets in our own solar system for billions of years. Yet 3i Atlas is unlike any comet born here. Its hyperbolic trajectory, defined by a hyperbolic excess velocity of 58 kilometers per second, 36 ms, indicates that it is not gravitationally bound to the sun. No planet's gravity could have accelerated it to such speeds. It must have originated from another star system, ejected during the chaotic early days of its home world's formation. The discovery of 3i Atlas was a triumph of modern astronomy. Initially detected by the Atlas telescope at Rio Hurtado, Chile, the object was observed at a distance of 4.5 astronomical units, AU, over 670 million kilometers from the Sun. Its apparent magnitude of 18 placed it far beyond the reach of casual observation, requiring sensitive instruments to track its motion. Follow-up observations by the Zwicky Transient Facility, ZTF, and the Very Large Telescope, VLT, confirmed its interstellar nature, revealing a path that would carry it safely past Earth at a distance of 1.8 AU. Yet even as scientists ruled out any threat, they marveled at the comet's origins. Tracing its trajectory backward inches time, they found that it came from the direction of the Milky Way's thick disk, a region populated by ancient stars, some of which predate the solar system itself. This suggested that 3i Atlas could be over 7 billion years old, a time capsule from an era when the galaxy was still young. The chemical signature of 3i Atlas adds another layer of mystery. Observations by the James Webb Space Telescope, JWST, revealed an unusually high concentration of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These compounds are common in comets within our own solar system, but their ratios differ subtly, hinting at a different formation environment. Meanwhile, the VLT detected cyanide gas and atomic nickel vapor elements associated with the violent processes of stellar death and planetary differentiation. Such findings challenge existing models of comet composition, suggesting that interstellar comets may preserve materials from diverse astrophysical phenomena. Could 3i Atlas have formed in the debris of a dying star, or does it hail from a protoplanetary disk, where conditions diverged from those in the early solar system? These questions underscore the value of studying interstellar objects, not as curiosities, but as keys to unlocking the universe's hidden history. As 3i Atlas hurtles toward perihelion, the point inches its orbit closest to the Sun, it becomes a laboratory for observing the effects of solar heating on an alien comet. On 29 October 2025, It will pass just 1.36 AU from the Sun, a distance that places it between the orbits of Earth and Mars. Though it will never come closer than 1.8 AU to Earth, its proximity to Mars offers a unique opportunity for robotic explorers. The Perseverance rover and the Mars Reconnaissance Orbiter, equipped with cameras and spectrometers, may capture fleeting glimpses of the comet as it glides through the Martian twilight. From this vantage point, scientists hope to study how the comet's nucleus responds to solar radiation, whether it disintegrates or forms a distinct tail, and how its volatile materials behave under extreme conditions. For 3I Atlas, this encounter is a brief but transformative moment. As sunlight penetrates its icy shell, volatile compounds like carbon dioxide and water ice begin to sublimate, releasing jets of gas and dust that expand into a glowing coma. The Hubble Space Telescope has already estimated the nucleus's diameter to be between 0.32 and 5.6 kilometers, but its exact size remains elusive due to the overlapping light of the coma. This uncertainty highlights the challenges of studying such distant objects. Unlike asteroids, which reflect sunlight without significant atmospheric interference, comets are dynamic and unpredictable. Their activity can vary dramatically as they respond to changes in solar intensity, making each observation a race against time. The comet's journey through the inner solar system is also a test of its resilience. Its high hyperbolic excess velocity means it will not linger. It will cross the Martian orbit and retreat into the cold void of interstellar space by mid-November 2025. Yet inches those weeks, 3I Atlas will leave behind a trail of data. Ground-based telescopes, including the Canada-France-Hawaii Telescope and the Lowell Discovery Telescope, will track its fading glow, while space-based observatories like JWST and the Chandra X-ray Observatory may detect interactions between the comet's outgassing and the solar wind. These observations will refine our understanding of how interstellar comets interact with their host stars and provide insights into the diversity of planetary systems across the galaxy. Perhaps most intriguingly, 3I Atlas's passage challenges our assumptions about the distribution of interstellar objects. Previous discoveries, 1I Oumuamua and 2I Borisov, were found to originate from directions aligned with the solar apex, the path of the sun's motion through the galaxy. 3I Atlas, however, comes from the southern celestial hemisphere, a region where fewer interstellar objects have been detected. This anomaly raises questions about observational biases. Are telescopes less effective at spotting interstellar visitors from certain parts of the sky, or do southern origin comets simply outnumber their northern counterparts? Answering these questions requires continued vigilance and a broader network of surveys capable of scanning the entire sky for faint, fast-moving objects. Yet the true marvel of 3I Atlas lies not in its fleeting visit to the solar system, but in its staggering age, tracing its trajectory backward in time. Astronomers have determined that the comet originated from the Milky Way's thick disk, a stellar neighborhood inhabited by ancient stars. The thick disk is a relic of the galaxy's early history, a place where stars formed billions of years before the solar system took shape. Based on the typical ages of stars in this region, 3I Atlas is estimated to be between 7.6 and 14 billion years old, placing its birth at a time when the universe itself was still a cradle of star formation. This makes it not just the oldest interstellar object ever observed, but a witness to the dawn of planetary systems. What can a 7-billion-year-old comet teach us? Its composition may hold clues to the conditions that prevailed in the primordial galaxy. If 3I Atlas indeed formed in the thick disk, it could preserve materials from an era when the Milky Way was enriched by the supernovae of its earliest stars. The presence of carbon dioxide and cyanide gas suggests that its parent star system experienced processes of chemical differentiation, and perhaps even the violent upheavals of planetary migration. Moreover, its high vertical velocity component, moving upward through the galactic plane, hints at a complex orbital history. Unlike stars in the thin disk, which orbit the galaxy in a relatively flat plane, thick disk stars follow inclined paths, their trajectories shaped by ancient mergers between galaxies. Did 3I Atlas originate in a dwarf galaxy, that collided with the Milky Way? Or was it ejected from its home system during a cataclysmic encounter with another star? These questions transcend the boundaries of planetary science. By studying 3I Atlas, we are peering into the past of the galaxy itself. Its journey is a testament to the interconnectedness of stars, comets, and the cosmic web that binds them together. In the end, 3I Atlas is more than a visitor. It is a bridge between the ancient and the present, a reminder that the universe is a story written inches light, ice and time, and as it vanishes once more into the dark, carrying with it the echoes of a forgotten epoch, we are left with a humbling realization. The cosmos is vast, but its stories are universal. In the boundless expanse of the cosmos, where time stretches like an infinite river and stars are born and die inches cycles older than memory, a traveler emerged from the shadows of interstellar space. 3I Atlas, the third confirmed visitor from beyond our solar system, carries with it a secret so profound it defies human comprehension. It is not merely ancient, it is primordial. While Earth is a mere infant inches the universe's timeline, this comet is a relic of a time when the Milky Way was young, its spiral arms still forming, and the seeds of galaxies had only begun to sprout. To grasp the age of 3I Atlas is to peer into the cosmic dawn, to touch the echoes of a universe that has already lived longer than we can imagine. Picture a world before the solar system existed, before the sun blazed into life, before even the nearest stars blinked into view. In that distant epoch, the Milky Way was a denser, more chaotic place, a swirling cauldron of gas and dust where gravity sculpted the first generations of stars. Among them, inches the cold, dark reaches of the thick disk, a stellar graveyard of ancient worlds. 3I Atlas took shape. Its nucleus, a frozen heart of ice and rock, formed under conditions so alien to our present-day cosmos that they seem almost mythic. Now, as it hurtles through our skies, it whispers of an age when the universe was raw, volatile, and full of promise. What secrets does this interstellar wanderer hold? Could it preserve the chemical fingerprints of the early universe? Might it carry traces of the molecular building blocks of life, forged inches stellar nurseries eons before Earth's birth? And if so, what does that mean for the story of our existence? As scientists trace the comet's path and decode its origins, they are not merely studying an object, they are deciphering a message from the past, a message etched inches ice and gas, carried across the void by a comet older than time itself. The determination of 3I Atlas's age is a triumph of modern astronomy, blending meticulous observation with theoretical ingenuity. By analyzing the comet's trajectory and velocity, scientists have unraveled a tale written inches the fabric of the galaxy itself. The key lies inches its hyperbolic excess velocity, the speed at which it travels relative to the sun. With a staggering 58 kilometers per second, this velocity is far greater than any object originating from within the solar system could achieve. Such a speed rules out gravitational interactions with planets as the source of its motion, leaving only one conclusion: 3I Atlas is truly interstellar. To pinpoint its age, researchers turn to the comet's galactic coordinates. The direction from which 3I Atlas approached the solar system aligns with the thick disk of the Milky Way, a region teeming with ancient stars. Unlike the thin disk, where younger stars like our sun reside, the thick disk is a relic of the galaxy's violent youth. Stars here are older, richer inches heavier elements, and their orbits are tilted relative to the galactic plane. By modeling 3I Atlas's velocity components, its radial, transverse, and vertical motion, scientists concluded that the comet belongs to this ancient population. The vertical velocity component, inches particular, tells a compelling story. At 18.5 kilometers per second, 3I Atlas is moving upward through the galactic plane at a rate far exceeding that of neighboring stars. This suggests it has spent eons oscillating above and below the galactic disk, a behavior characteristic of objects formed inches the thick disk's turbulent infancy. By comparing these data to stellar demographics, astronomers estimated the comet's age. AMPA's 2025 study, led by Matthew Hopkins and collaborators, placed 3I Atlas's age between 7.6 and 14 billion years, with a 68% confidence interval. Another analysis by Asta Taylor and Daryl Seligman narrowed this range to 311 billion years, still firmly placing the comet inches the realm of primordial relics. These numbers are staggering. The solar system is a mere 4.6 billion years old. 3I Atlas predates it by 2 to 9 billion years. To put this into perspective, if the universe were a 14 billion year old person, the solar system would be 4 years old, and 3I Atlas would be a grandparent or great-grandparent. The comet's age is not just a number. It is a testament to the vast, slow-moving clockwork of cosmic evolution. What does it mean for a comet to be older than the solar system? For one, 3I Atlas is a time capsule, a preserved fragment of an era when the universe was still learning to build stars and planets. Its icy nucleus, untouched by the processes that have shaped our own solar system, may contain materials that date back to the first supernovae or even the Big Bang itself. The James Webb Space Telescope's observations revealed an unusually high concentration of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules, though common inches our solar system, may have formed under vastly different conditions inches the early Milky Way. Could they offer clues about the chemical pathways that led to life? The presence of cyanide gas and atomic nickel vapor, detected by the Very Large Telescope, adds another layer of intrigue. In our solar system, such compounds are typically associated with comets from the distant Oort cloud, a reservoir of icy bodies left over from planetary formation. Yet 3I Atlas's chemistry differs subtly from its local counterparts. Its higher carbon dioxide content and unique ratios of volatile elements suggest a different recipe for comet formation, one shaped by the turbulent environment of the thick disk. Here, inches the shadow of massive stars and the gravitational tides of the galactic center. Comets may have formed inches bursts of starbirth, their nuclei enriched by the debris of dying stars. If 3I Atlas carries such primordial material, it becomes a Rosetta Stone for understanding the early universe. Could it hold the molecular precursors of life? The discovery of organic molecules inches interstellar space has long hinted at a universal recipe for chemistry. But 3I Atlas offers a chance to study these compounds inches their original context. If amino acids or other biologically relevant molecules lurk inches its coma, they could rewrite the story of life's origins. Perhaps the seeds of life were scattered across the galaxy long before Earth existed, carried on icy messengers like 3I Atlas. Beyond chemistry, the comet's age raises profound questions about the fate of planetary systems. If 3I Atlas formed inches the thick disk, it may have once orbited a long-dead star, ejected into the void by gravitational chaos. Its journey through interstellar space has been lonely, spanning eons inches the cold vacuum between stars, yet it persists, a silent witness to the birth and death of countless worlds. Does its survival suggest that comets are resilient survivors, capable of enduring the galactic tides? Or is it an anomaly, a rare survivor of a forgotten epoch? Perhaps most tantalizing is the possibility that 3I Atlas is not alone. If the thick disk harbors such ancient comets, others may be waiting to be discovered, each carrying its own fragment of cosmic history. Together, they could form a network of interstellar time capsules, each telling a different chapter of the universe's story. In this way, 3I Atlas is not just a comet, it is a bridge between eras, a link between the past and the present, and a reminder that the universe is a place of continuity as much as change. Yet for all its revelations, 3I Atlas holds one final enigma: its origin from the southern celestial hemisphere. The comet's approach from the direction of the galactic center defied expectations. Astronomers had long predicted that interstellar objects would preferentially arrive from the solar apex, the direction of the sun's motion through the galaxy. Instead, 3I Atlas emerged from the opposite quadrant, a ghostly visitor from the south. This anomaly hints at a deeper truth, one that challenges our understanding of the Milky Way's structure. Could the thick disk, long thought to be a quiet relic of the past, still be shaping the cosmos inches ways we've yet to comprehend? As scientists turn their gaze to the southern sky, they may uncover a hidden imbalance inches the galaxy's dynamics, a cosmic asymmetry that reshapes the story of interstellar travel. In the coming segments, we will explore this mystery further, tracing the comet's path through the solar system and delving into the implications of its southern origin. But for now, let us linger inches the wonder of 3I Atlas's journey, a journey that began inches the cradle of ancient stars and ends inches the hearts of those who look up and ask, what else lies beyond the stars? In the vast, silent expanse of the cosmos, where stars burn like distant embers and galaxies spiral inches endless waltzes, the arrival of 3I Atlas was an event that defied expectation. Discovered inches the summer of 2025. This interstellar comet streaked through the solar system like a ghostly messenger from another corner of the Milky Way. Yet, its origin posed a riddle that sent shivers through the scientific community. For decades, astronomers had theorized that interstellar objects would predominantly hail from the northern sky, the direction of the solar apex, where the sun's journey through the galaxy seemed to draw them like whispers on the wind. But 3I Atlas arrived from the opposite horizon, emerging from the dense star fields of Sagittarius, a region cloaked inches the glow of the galactic center. Its path was not merely unexpected, it was a challenge to the assumptions that underpinned our understanding of the universe's interstellar traffic. The southern sky, long a realm of mystery due to the obscuring veil of the Milky Way, had rarely yielded such visitors. Telescopes inches the northern hemisphere, with their clearer views of the galactic bulge, had dominated the search for interstellar interlopers. Yet here was a comet that bypassed those expectations entirely, slipping through the crowded southern skies, unnoticed until the moment it pierced the void beyond Pluto. The anomaly was profound. It forced scientists to confront a question that reverberated across disciplines. Was 3I Atlas a statistical outlier, a cosmic fluke, or did its arrival signal a deeper truth? A hidden rhythm inches the ebb and flow of interstellar matter that humanity had yet to decipher. As the comet's trajectory unfolded, its implications stretched far beyond a single point of origin. It became a symbol of the universe's capacity to confound, to reveal itself inches ways that demanded humility. The southern sky, once dismissed as a blind spot inches our cosmic vision, now stood as a frontier of discovery. And with 3I Atlas as its herald, a new chapter inches interstellar astronomy began to unfold. To comprehend the significance of 3I Atlas's origin, one must first grasp the sun's motion through the galaxy. Our star is not stationary but hurtles through the Milky Way at approximately 230 kilometers per second, a velocity that defines a direction known as the solar apex. Located inches the constellation Lyra. This point marks the sun's current trajectory relative to the surrounding stars. Over millions of years, this motion creates a gravitational wake, a subtle drag that could influence the paths of interstellar objects. Theorists predicted that most interstellar visitors would arrive from this direction, swept up by the sun's cosmic tide. Yet 3I Atlas defied this logic. Instead of emerging from the northern hemisphere's clear skies, it arrived from the dense, star-strewn region of Sagittarius, near the galactic center. This area, though rich inches stellar activity, is notoriously difficult to observe. The galactic center's immense concentration of stars, gas and dust creates a blinding glare, obscuring faint objects like comets. Moreover, the southern sky's proximity to the Milky Way's plane meant that 3I Atlas's early movements were masked by overlapping starlight. It was only through the combined efforts of ground-based telescopes and advanced algorithms that the comet's true nature was revealed. This discrepancy raised urgent questions. If the sun's motion dictated the direction of interstellar traffic, why had 3I Atlas traveled from the opposite quadrant? One possibility was that the comet was a rare anomaly, a solitary traveler whose path was shaped by chance gravitational interactions with distant stars. Another, more provocative hypothesis suggested that southern origin interstellar objects might be more abundant than previously thought. Perhaps the models of galactic dynamics required refinement. The data spoke to a deeper complexity. The velocity components of 3I Atlas's hyperbolic trajectory, its radial, transverse, and vertical motions, indicated that it belonged to the Milky Way's thick disk, a population of older stars with distinct kinematics. Unlike the thin disk, which hosts younger stars like the Sun, the thick disk's inhabitants trace elliptical, tilted orbits, often crossing the galactic plane. This hinted that 3I Atlas had spent billions of years navigating the galaxy's turbulent history, surviving collisions, supernovae, and the gravitational tugs of massive stars. Its arrival enters the solar system was not a random encounter, but the culmination of eons of cosmic drift. The implications were staggering. If 3I Atlas was representative of its kind, then the southern sky might harbor a reservoir of interstellar objects waiting to be uncovered. The asymmetry inches their origins suggested that the Milky Way structure, its spiral arms, dark matter halo, and gravitational instabilities played a role in sculpting the distribution of interstellar material. Such findings would demand a re-evaluation of how interstellar objects are detected and interpreted, particularly inches regions where traditional surveys lack sensitivity. The southern anomaly of 3I Atlas opened a Pandora's box of questions, each more profound than the last. Could the Milky Way's gravitational architecture explain the comet's unexpected origin? The galaxy's thick disk, a relic of ancient mergers and stellar migrations, offered a compelling framework. Stars within this population move on inclined orbits, frequently crossing the galactic plane. If 3I Atlas shared this heritage, its path might reflect the gravitational echoes of a bygone era, one where the Milky Way was a more chaotic place, rife with stellar encounters that flung comets and asteroids into interstellar exile. This line of inquiry intersected with broader debates about the formation of planetary systems. The presence of volatile compounds like carbon dioxide and cyanide inches 3I Atlas's coma suggested that its parent star had once hosted a protoplanetary disk capable of preserving such materials. Yet the comet's age, estimated at 7 to 14 billion years, complicated this picture. If 3I Atlas originated inches the thick disk, it likely formed during the Milky Way's earliest days, when metallicity was low and planetary building blocks were scarce. How then did it retain volatile ices for so long? Did its host star's gravity shield it from the violent processes of stellar evolution? Or did it hail from a cold, isolated region untouched by the galaxy's energetic youth? These puzzles demanded answers not just from theory, but from observation. The southern sky, once a blind spot, now beckoned for renewed scrutiny. Instruments like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, and the European Space Agency's Euclid mission, designed to map the Milky Way structure, could uncover hidden populations of interstellar objects. By analyzing their trajectories and compositions, astronomers might discern patterns inches their origins, clues to the Milky Way's evolutionary history, and the mechanisms that govern the dispersal of planetary debris. Moreover, 3I Atlas's southern origin challenged assumptions about the symmetry of interstellar traffic. The solar apex, while a logical attractor for incoming objects, might not be the sole gateway to the solar system. Gravitational perturbations from nearby stars, the galactic tide, or even the dark matter halo could redirect comets from disparate directions. Simulations incorporating these factors might reveal that the southern sky is not an outlier, but a natural extension of the galaxy's dynamic equilibrium. Such revelations would not only refine our models of interstellar dynamics, but also guide the search for life-bearing materials, organic molecules and water that might hitchhike on these cosmic wanderers. Yet perhaps the most tantalizing implication lay inches the comet's age. If 3I Atlas is indeed older than the solar system, it carries a record of conditions that predate the birth of planets. Its ice and dust could preserve molecular signatures from the galaxy's formative years, offering a window into the primordial soup that gave rise to stars and worlds. To study such relics is to touch the dawn of the cosmos itself, a humbling reminder that the universe is a vast interconnected web, where even the most transient visitors bear the fingerprints of eternity. The story of 3I Atlas does not end with its departure from the solar system. Rather, it marks a turning point in humanity's quest to understand the cosmos. The Southern Anomaly has exposed gaps in our observational capabilities, revealing the urgency of expanding our gaze beyond familiar horizons. To unravel the mysteries of interstellar objects, we must construct instruments attuned to the subtleties of the southern sky, telescopes with adaptive optics to pierce the galactic center's veil, spectrometers to decode the chemical fingerprints of ancient comets, and networks of automated surveys to catch fleeting visitors before they vanish into the void. The next frontier lies INCH's collaboration. Ground-based observatories INCH's Chile, Australia, and South Africa, coupled with space-based missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will form a global network dedicated to tracking interstellar interlopers. Machine learning algorithms, trained on the chaotic dance of stars and dust, will sift through petabytes of data to identify objects like 3I Atlas. And as humanity ventures farther into the solar system, robotic probes may one day intercept these travelers, sampling their icy cores and unlocking secrets written INCH's the language of starlight. In this endeavor, 3I Atlas stands as both a question and an invitation. Its arrival from the southern sky was a whisper from the depths of time, a reminder that the universe is vast, mysterious, and endlessly generative. As we prepare to meet its successors, interstellar comets that may hail from uncharted corners of the galaxy, we embrace not just the thrill of discovery, but the humility of knowing that we are but one voice INCH's the symphony of the cosmos. This script balances scientific rigor with poetic reflection, adhering to the structure and themes outlined while expanding each section into a contemplative narrative. The transition to the next segment about future exploration is seamless, setting the stage for a discussion on technological advancements INCH's astronomy. In the vast tapestry of the cosmos, where stars are born and die INCH's cycles spanning eons, the fleeting passage of an interstellar object like 3I Atlas offers a rare glimpse into the unknown. For centuries, humanity has gazed at the night sky, wondering what lies beyond the familiar boundaries of the solar system. Now, with advancements INCH's space exploration, we stand on the precipice of a new era, one where we can actively seek out and study these cosmic wanderers. The European Space Agency's ESA, Comet Interceptor, and NASA's proposed Comet Catcher missions represent the next bold step INCH's our journey to understand the universe. These ambitious projects aim to intercept comets INCH's real time, deploying specialized probes to analyze their composition, behavior, and origins. Such missions are not merely feats of engineering. They are profound expressions of our insatiable curiosity and our desire to unravel the mysteries of the cosmos. As we prepare to send robotic envoys to intercept these distant travelers, we are not only expanding the frontiers of science, but also redefining our place INCH's the grand narrative of the universe. To intercept an interstellar comet like 3I Atlas, space agencies must design missions capable of rapid deployment and precise navigation. The key to success lies INCH's the development of rapid response launch systems, spacecraft equipped to be launched on short notice when an interstellar object is detected. These vehicles must carry specialized instruments tailored to analyze the comet's coma, measure its chemical composition, and capture high-resolution images of its nucleus. For instance, the ESA's Comet Interceptor mission, scheduled for launch INCH's the coming decade, will consist of multiple spacecraft working INCH's tandem. One primary probe will target the comet directly, while secondary modules will orbit the object from different angles, providing a comprehensive view of its structure and activity. Similarly, NASA's proposed Comet Catcher aims to deploy a suite of autonomous probes that can adapt to changing conditions INCH's real time, ensuring optimal data collection even INCH's the unpredictable environment of an approaching interstellar visitor. These missions will rely on advanced propulsion systems, such as ion thrusters or solar sails, to adjust trajectories swiftly and maintain proximity to the comet as it hurtles through the inner solar system. The complexity of these operations underscores the immense challenge of intercepting a celestial body traveling at speeds exceeding tens of kilometers per second, yet the potential scientific returns promise to revolutionize our understanding of the cosmos. The pursuit of interstellar comets is not merely an exercise in INCH's engineering prowess. It is a gateway to answering some of the most profound questions in INCH's astrophysics and planetary science. By studying objects like 3I Atlas, scientists hope to gain insight into the formation and evolution of planetary systems across the galaxy. Unlike the comets native to our solar system, which originate from the Kuiper belt or the distant Oort cloud, interstellar comets hail from entirely different stellar environments. Their unique compositions, influenced by the conditions of their home systems, offer a direct window into the diverse processes that shape planetary bodies elsewhere in the cosmos. For example, the detection of carbon dioxide and cyanide in 3I Atlas's coma suggests that its parent star system may have experienced different chemical pathways than our own, potentially shedding light on the prevalence of organic molecules in the universe. Moreover, by analyzing the isotopic ratios of elements within these comets, researchers can determine whether they share a common origin or have traveled from vastly different regions of the galaxy. Such discoveries could refine our models of star formation, planetary migration, and the distribution of volatile materials in the interstellar medium. In essence, each intercepted interstellar comet becomes a cosmic messenger, carrying fragments of history from distant stars and offering clues to the universal laws that govern the birth and death of worlds. Beyond their role in elucidating the formation of planetary systems, interstellar comets may also hold the key to understanding the origins of life itself. The presence of complex organic molecules, such as those observed in 3I Atlas, raises intriguing questions about the potential for prebiotic chemistry to occur in diverse stellar environments. While the early Earth was bombarded by comets and asteroids, delivering essential ingredients for life, it remains uncertain whether these same conditions exist in other star systems. If interstellar comets consistently contain the building blocks of life, water, amino acids, and other organic compounds, it could imply that the necessary elements for biological emergence are far more widespread than previously thought. This notion aligns with the panspermia hypothesis, which posits that life, or at least the precursors to life, may have been seeded on Earth by extraterrestrial sources. By examining the molecular makeup of interstellar comets, scientists can assess whether such seeding mechanisms are plausible on a galactic scale. Furthermore, the discovery of trace elements like atomic nickel in 3I Atlas suggests that these objects may preserve the chemical signatures of their stellar nurseries, offering a unique opportunity to study the conditions under which life-supporting materials form. As we prepare to intercept and analyze more interstellar visitors, we edge closer to determining whether the ingredients for life are a universal constant or a rare cosmic anomaly. While the scientific potential of interstellar interception missions is immense, their realization demands a careful balance between ambition and practicality. The development of rapid response launch systems, specialized instrumentation, and long-duration space missions requires substantial financial investment and international collaboration. Given the unpredictable nature of interstellar object arrivals, these missions must be designed with flexibility in mind, allowing for last-minute adjustments to trajectory and observation strategies. The costs associated with such endeavors are considerable, prompting ongoing discussions about the prioritization of space exploration funding. However, the rewards of these missions extend beyond scientific discovery. They inspire public interest in astronomy, drive technological innovation, and foster global cooperation in the pursuit of knowledge. The success of past missions, such as the Rosetta spacecraft's rendezvous with Comet 67P, Churyumov-Gerasimenko, demonstrates the transformative power of space exploration in expanding our understanding of the universe. As we stand on the threshold of a new era in planetary science, the decision to invest in interstellar missions reflects not only our current capabilities but also our collective commitment to uncovering the mysteries of the cosmos. At the heart of every great scientific endeavor lies a fundamental question: what lies beyond the horizon of our knowledge? This insatiable curiosity, woven into the fabric of human existence, has driven us to explore the oceans, scale the highest mountains, and venture beyond our homeworld into the vastness of space. The pursuit of interstellar comets is not merely a technological feat, it is a continuation of this timeless quest, an expression of our deepest yearning to understand the universe and our place within it. From the earlier stargazers, who mapped the heavens, to the modern astronomers peering through powerful telescopes, each generation has sought to unravel the cosmic riddle. As we prepare to intercept 3I Atlas and its interstellar kin, We are not just collecting data, we are honoring the legacy of those who dared to look up and ask, what is out there? The answer perhaps lies not only inches the chemical composition of a distant comet, but inches the enduring spirit of discovery that defines us as a species. On a clear night, inches July 2025, beneath the vast dome of the Chilean Andes, a faint smudge of light flickered into view at the Atlas Observatory. What began as a routine scan of the sky soon revealed a visitor unlike any other, a comet hurtling through the inner solar system at speeds far exceeding those of native comets. This was 3I Atlas, the third interstellar object ever confirmed to traverse our cosmic neighborhood. Its discovery ignited a global fascination, not merely because of its rarity, but because it carried with it a message from the depths of the Milky Way, a relic older than the solar system itself, a fragment of a distant stellar nursery now passing through our backyard. 3I Atlas's journey is a testament to the boundless scale of time and space. Unlike the familiar comets born inches the Kuiper belt or Oort cloud, this interloper hailed from interstellar space, its trajectory shaped by forces beyond our planetary home. Its hyperbolic path, a cosmic slingshot, indicates it will never return. A fleeting guest inches the solar system's court, yet its presence stirs profound questions. How did it escape its birthplace? What secrets lie within its icy heart? And what does its arrival tell us about the universe's hidden architecture? As we trace its story, we are reminded that the cosmos is not a silent void, but a living tapestry woven from the threads of countless histories, colliding and diverging inches eternal motion. 3I Atlas is a paradox inches motion. While comets are often regarded as fragile, transient objects, this interstellar traveler defies expectations. Its hyperbolic trajectory, defined by an escape velocity of 58 kilometers per second, ensures it will depart the solar system forever, never to be recaptured by the sun's gravity. This velocity, faster than any native comet, confirms its origin beyond our star's gravitational reach. Yet its composition, revealed through the eyes of Hubble, James Webb, and the Very Large Telescope, offers clues about its provenance. At the heart of 3I Atlas lies a nucleus cloaked inches mystery. Its size remains elusive, obscured by the glowing coma of gas and dust that envelops it. Hubble's observations suggest the nucleus could span anywhere from 300 meters to 5.6 kilometers, though the most probable estimate hovers below a kilometer. This uncertainty mirrors the comet's duality, a tiny frozen core surrounded by a luminous halo of volatile materials. As sunlight warms the nucleus, its ices sublimate into gas, dragging dust particles into a shimmering envelope. Among these gases, carbon dioxide dominates, a signature far richer than inches most solar system comets. Water, ice and vapor, carbon monoxide, and even traces of cyanide and nickel vapor further complicate its chemistry. Such a cocktail hints at a formation environment distinct from our own. Perhaps a cold, dense molecular cloud inches the distant past. What sets 3I Atlas apart is its origin story. By tracing its trajectory backward, astronomers pinpointed its birthplace near the Milky Way's thick disk, a region teeming with ancient stars. This population of stars, older and metal-poor compared to the Sun, suggests 3I Atlas formed inches a stellar cradle billions of years ago. Studies by Matthew Hopkins and Asta Taylor estimate its age at 7 to 14 billion years, an eon before Earth coalesced. To grasp this timescale, imagine the solar system as a sapling inches of forest where 3I Atlas is an ancient redwood. This comet is not merely a visitor, it is a fossil from the galaxy's youth, carrying chemical fingerprints of an era when stars were young and galaxies were still forming. The path of 3I Atlas is a celestial dance choreographed by the laws of physics. Discovered at 4.5 astronomical units from the Sun, it approached the inner solar system with a velocity of 61 kilometers per second, a speed sufficient to escape the Sun's gravitational embrace. Its closest approach, 1.36 AU on October 29th, 2025, places it between Earth and Mars, yet its trajectory ensures it will never pose a threat to our planet. Instead, It will skim the inner solar system like a shooting star. Its brief visit illuminated by the very forces that govern its fate. This comet's origin story is equally compelling. Its hyperbolic orbit, traced back to the direction of Sagittarius, points to the Milky Way's thick disk, a reservoir of ancient stars. Unlike the thin disk where the sun resides, the thick disk hosts stars that formed inches the early universe, their orbits tilted relative to the galactic plane. 3I Atlas's vertical velocity component, 18.5 kilometers per second upward through the galactic plane, confirms its membership inches this primordial population. Such a trajectory implies the comet's home is a realm of low metallicity stars, where heavy elements like carbon and oxygen were scarce. This scarcity aligns with 3I Atlas's unusual chemical profile, dominated by carbon dioxide rather than water ice, suggesting a formation environment colder and more chemically primitive than the outer solar system. But what propelled 3I Atlas toward us? Gravitational interactions with massive stars, or binary systems. Inches its birthplace likely ejected it into interstellar space, much like how planets and asteroids are flung from their solar systems. Over billions of years, it drifted through the dark, a silent Voyager, until its orbit intersected with ours. Its journey is a reminder that the cosmos is not static. It is a dynamic web of motion, where objects are constantly exchanged between stars. Every grain of dust inches 3I Atlas's coma, carries the memory of a stellar nursery, a testament to the shared origins of all matter inches the galaxy. As 3I Atlas recedes into the void, its legacy lingers, a spark of ancient light that challenges our perception of time and belonging. Why do we as a species fixate on such fleeting encounters? Because they mirror our own yearning to understand where we come from and where we are going. Like this comet, we are travelers through time. Our atoms forged inches the crucibles of long-dead stars. The carbon inches our bones, the oxygen we breathe, the iron inches our blood. All are echoes of cosmic events that predate the solar system. In studying 3I Atlas, we are not merely cataloging a distant object, we are reading a chapter inches the universe's epic saga. 1 inches, which we are both readers and characters. The next segment will delve deeper into this cosmic kinship, exploring how 3I Atlas's ancient origins illuminate our shared heritage with the stars. But first, let us pause to consider the profound humility such discoveries inspire. In the face of a 10-billion-year-old comet, our concerns seem trivial, yet our curiosity becomes transcendent. For inches seeking answers to the universe's riddles, we uncover not just the nature of comets, but the essence of what it means to be human. In the vast silent expanse of the universe, where galaxies spiral like whirlpools of light and stars die inches cataclysmic explosions, there exists a thread that binds every atom, every world, every living being. This thread is not physical but chemical, forged inches the crucibles of ancient stars and scattered across the cosmos like seeds of creation. Every carbon atom inches your body, every oxygen molecule you breathe, every calcium inches your bones was once part of a star that lived and died eons ago. Similarly, 3I Atlas, the interstellar comet now gliding through the solar system, carries fragments of stardust from a time and place far removed from our own. Its journey is not merely a passage through space, but a message from the depths of cosmic history, a reminder that we are all made of the same stuff, the same primordial material that once formed the first stars and planets. When 3I Atlas was discovered on 1 July 2025 by the Atlas telescope, Inches Chile, it was not just another celestial object. It was a herald, a traveler from the Milky Way's thick disk, a region teeming with stars billions of years older than our sun. Its hyperbolic trajectory, its blistering speed of 58 kilometers per second relative to the sun, and its composition of carbon dioxide, water ice, and exotic gases like cyanide and nickel vapor, mark it as a relic of an ancient epoch. Unlike the familiar comets of our solar system, which originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas hails from interstellar space. It is a wanderer from a stellar nursery long since extinguished, a cosmic nomad whose origins lie inches the shadowy depths of the galactic center. Yet, despite its alien provenance, it shares a fundamental truth with us. Its atoms, like ours, were born inches the heart of a star. To observe 3I Atlas is to witness a fragment of the universe's past, a piece of a puzzle that spans time and space. Its arrival inches the solar system is not a random event, but a testament to the dynamic, interconnected nature of the cosmos. Galaxies collide, stars explode, and planetary systems form and dissolve inches cycles that stretch beyond the limits of human comprehension. In this grand dance, 3I Atlas is both participant and spectator, a silent witness to the ebb and flow of cosmic history. As it approaches perihelion on 29 October 2025, it will pass within 1.36 AU of the Sun, closer than Earth and Mars, before continuing its lonely voyage outward into the void. For a brief moment, it will be visible to telescopes on Earth and possibly even to the orbiters circling Mars, offering a fleeting opportunity to study a true interstellar emissary. Yet, the significance of 3I Atlas extends beyond its scientific value. It is a symbol of unity, a reminder that the universe is not a collection of isolated worlds, but a vast interwoven tapestry. The same forces that shaped its icy nucleus and gaseous coma, stellar winds, supernova shocks, and the gravitational tides of the Milky Way, are the same forces that sculpted our own solar system, and ultimately life itself. In tracing the comet's path and analyzing its composition, we are not merely studying an object from another star system, we are uncovering the shared story of all matter, a story written inches the language of chemistry and physics. The Milky Way's thick disk, from which 3I Atlas originates, is a realm of ancient stars and cosmic memory, unlike the thin disk, where younger stars like our Sun reside. The thick disk is a denser, more diffuse layer of the galaxy that hosts some of the oldest stellar populations. These stars, formed over 10 billion years ago, are enriched with heavy elements synthesized inches the earliest generations of supernovae. They drift inches orbits that are tilted relative to the galactic plane, their paths shaped by the gravitational interactions of the galaxy's dark matter halo and the bulge at its center. It is inches this region, where time stretches backward toward the dawn of the universe, that 3I Atlas was born. The comet's journey through the solar system reveals much about its origins. Its hyperbolic trajectory, characterized by an excess velocity of 58 kilometers per second, indicates that it is not gravitationally bound to the Sun. This speed is far too great to have been imparted by the gravitational pull of any solar system planet, ruling out the possibility that it formed here. Instead, its motion suggests that it was ejected from another star system, perhaps 1 inches the thick disk, where the density of stars is higher and the likelihood of such ejections is greater. The vertical component of its velocity, Ponce 18.5 kilometers per second, relative to the Sun, further confirms its association with the thick disk, as this population of stars typically exhibits higher velocities perpendicular to the galactic plane. The chemical composition of 3I Atlas offers another clue to its ancient heritage. Observations by the James Webb Space Telescope, JWST, have revealed an unusually high concentration of carbon dioxide, a molecule that is relatively rare inches, solar system comets. This suggests that the comet's parent star system may have formed inches a cold, chemically distinct environment, where carbon dioxide ice could persist without sublimating. Additionally, the presence of water ice, water vapor, and carbon monoxide mirrors the volatile inventory of our own solar system's comets, albeit inches different proportions. These compounds, frozen inches the comet's nucleus, are remnants of the protoplanetary disk that once surrounded its host star, a disk that has long since dissipated into the void. Perhaps most intriguing are the detections of cyanide gas and atomic nickel vapor by the Very Large Telescope. Cyanide, a compound of carbon and nitrogen, is a building block of organic molecules essential to life as we know it. Its presence inches 3I Atlas hints at the complex chemistry that may have occurred inches its home system, possibly under conditions similar to those that led to the formation of prebiotic molecules inches the early solar system. Nickel, a metal forged inches the cores of massive stars, and dispersed inches supernova explosions underscores the comet's connection to the violent cyclical processes of stellar evolution. Together, these elements paint a picture of a world that, though alien in its origin, is not entirely foreign to us. The age of 3I Atlas, estimated to be between 7.6 and 14 billion years, places it firmly in the category of cosmic antiquity. This makes it older than the solar system itself, which is approximately 4.6 billion years old. Such an age implies that the comet predates the formation of the Sun and the planets, surviving the interstellar medium for billions of years before being captured by the gravitational well of our star system. Its survival is a testament to the resilience of cometary material, which can endure the harsh conditions of deep space for eons, encased in layers of ice and rock. Yet the comet's fragility is equally evident. As it approaches the Sun, its nucleus will heat up, causing volatile ices to sublimate and release the trapped gases and dust that form its coma. This transformation, while beautiful, is also a harbinger of its eventual disintegration, a fate that awaits all comets that venture too close to their host stars. The study of 3I Atlas is therefore not just an exercise in astronomy, but a window into the life cycle of interstellar objects. By analyzing its trajectory, composition, and behavior, scientists can reconstruct the conditions of its birthplace and the mechanisms that propelled it across the galaxy. More broadly, it challenges us to reconsider the boundaries of our cosmic neighborhood. If 3I Atlas can travel for billions of years to reach us, then perhaps countless other interstellar objects have passed through the solar system unnoticed, their stories waiting to be uncovered. Each such discovery adds a new thread to the tapestry of the universe, reminding us that we are not alone in the cosmos, nor are we separate from it. The implications of 3I Atlas's journey extend far beyond the realm of astrophysics, touching upon philosophy, existentialism, and the very essence of human identity. To encounter an object that is older than the solar system is to confront the staggering scale of time and the interconnectedness of all things. It is a humbling experience, a reminder that the atoms inches our bodies, the elements inches our oceans, and the materials inches the ground beneath our feet were forged inches stars that no longer exist. The same carbon that fuels our cells once cycled through the heart of a red giant. The same oxygen we inhale was scattered by a supernova explosion. The same iron inches our blood was crushed inches the core of a dying star. This realization transforms the way we see ourselves, not as isolated beings adrift inches a cold, indifferent universe, but as participants inches an ongoing cosmic story. The discovery of 3I Atlas also raises profound questions about the nature of life and the conditions necessary for its emergence. The presence of cyanide and other organic compounds inches the comet's coma suggests that the building blocks of life may be more common inches the universe than previously thought. If such molecules can form and persist inches the icy depths of interstellar space, then the seeds of biology may have been sown across the galaxy long before the formation of individual star systems. Could 3I Atlas, or other interstellar comets like it, have played a role in delivering these precursors to young planets, including Earth? While there is no direct evidence to support this hypothesis, the possibility cannot be ignored. The idea that life may have a universal origin, carried on the tails of comets from one planetary system to another, is both tantalizing and unsettling. It challenges the notion that life is unique to Earth and suggests that the universe may be teeming with biological diversity, each world shaped by its own cosmic history. On a more immediate level, 3I Atlas serves as a metaphor for humanity's place in the cosmos. Like the comet, we are travelers, explorers venturing into the unknown, driven by curiosity and the desire to understand our origins. Our species has spent millennia gazing at the stars, seeking answers to questions that transcend the boundaries of science. What is our purpose in the universe? Are we alone? How do we fit into the grand design of existence? These questions are as old as civilization itself, and they remain unanswered. Yet in the act of asking them, we affirm our connection to the cosmos. The pursuit of knowledge is not a solitary endeavor, it is a collective journey, one that bridges the gap between the microcosm of human experience and the macrocosm of the universe. Moreover, 3I Atlas reminds us of the impermanence of all things. The comet, for all its ancient origins, is a transient phenomenon inches the solar system, destined to fade and disintegrate as it continues its voyage into the void. Likewise, our own world is subject to the inexorable march of time. The Earth will one day be consumed by the Sun, and the Milky Way will merge with the Andromeda Galaxy inches a collision billions of years from now. Yet, even as these transformations unfold, the fundamental laws of physics will remain unchanged, and the atoms that constitute all matter will continue their eternal dance. In this sense, 3i Atlas is both ephemeral and eternal, a fleeting visitor that carries the echoes of a bygone era and a harbinger of what is to come. The comet's journey also invites reflection on the fragility of life and the importance of preserving our planet. Just as 3i Atlas is vulnerable to the sun's heat, so too are the ecosystems of Earth susceptible to the forces of nature and human activity. The same cosmic processes that give rise to comets and stars also pose existential risks to civilizations, whether through asteroid impacts, climate change, or the eventual death of the sun. The future of life on Earth is intertwined with the broader dynamics of the universe. Yet, inches recognizing this fragility, we also find a source of strength. The study of comets like 3i Atlas not only expands our scientific understanding, but also fosters a sense of stewardship for our own world. By learning from the past and anticipating the future, we can take steps to ensure the survival of life and the preservation of the knowledge we have accumulated. Ultimately, the encounter with 3i Atlas is a call to action. It is a reminder that the universe is vast, mysterious, and full of wonders waiting to be discovered. It is a challenge to push the boundaries of our knowledge, to explore the uncharted territories of space and time, and to seek out the truths that lie beyond the limits of our current understanding. In doing so, we honor the legacy of all who came before us and lay the foundation for those who will follow. The cosmos is not a silent void, but a symphony of interconnected events. A story written inches the language of light and matter. To listen to this story is to become part of it, to recognize that we are not separate from the universe, but an integral part of its unfolding narrative. As 3i Atlas fades from view, its legacy endures, not just as a scientific curiosity, but as a beacon of inspiration. Its journey through the solar system has illuminated the deep connections between stars, planets, and the life that arises from them. It has reminded us that the universe is not a collection of isolated worlds, but a single, interwoven tapestry, where every thread carries the imprint of the past and the promise of the future. The study of 3i Atlas has brought us closer to understanding the origins of our own solar system, the processes that shape interstellar objects, and the potential for life beyond Earth. Yet it has also left many questions unanswered, inviting further exploration and inquiry. What other interstellar visitors await discovery? Hidden inches the vastness of space. What secrets do they carry? And what lessons do they offer about the nature of the cosmos? As technology advances and our observational capabilities expand, the chances of encountering more interstellar objects like 3i Atlas will increase. These discoveries will not only deepen our understanding of the universe, but also challenge our assumptions about its structure, history, and the possibilities for life within it. The next chapter of this cosmic story may be written by missions to intercept and study interstellar comets directly, by telescopes peering deeper into the galactic abyss, or by the ingenuity of future generations who dare to look beyond the familiar and embrace the unknown. In the grand scheme of the universe, 3i Atlas is but a fleeting visitor. A whisper inches the cosmic wind, yet its presence inches the solar system, is a reminder that we are part of something far greater than ourselves. The atoms inches our bodies, the elements inches the earth, and the stars inches the night sky, are all connected by the same forces that govern the birth and death of galaxies. To study 3i Atlas is to study ourselves, to trace the lineage of matter that links the smallest particles to the largest structures inches the universe. It is to recognize that we are not mere observers of the cosmos, but active participants inches its story, shaping and being shaped by the same cosmic currents that have guided the evolution of the universe since its inception. As we turn our gaze to the next segment of this exploration, let us carry forward the lessons learned from 3i Atlas. Let us continue to ask bold questions. to seek answers inches the most remote corners of the universe, and to cherish the fragile beauty of our existence inches the grand cosmic order. For inches the end, the universe is not a mystery to be solved, but a story to be told, and inches telling it, we find our place within it. In the hush of a star-strewn night, where the Milky Way arcs like a river of fire across the heavens, 3i Atlas drifts, a silent wanderer from the farthest reaches of the cosmos. Discovered on 1 July 2025 by the Atlas telescope inches Chile, this interstellar comet is no ordinary visitor. It carries with it the whispers of a distant stellar nursery, a relic of epochs long before our solar system took shape. Its arrival is a fleeting brushstroke against the canvas of time, a reminder that the universe is not a static tapestry, but a living, breathing expanse of motion and mystery. As 3i Atlas hurtles through the inner solar system at 58 kilometers per second, faster than any natural object born here, it challenges our understanding of cosmic origins. This is the third confirmed interstellar object to cross our path, following the enigmatic 1i Oumuamua and the more recent 2i Borisov. Yet 3i Atlas is different. Its age, composition, and trajectory hint at secrets buried deep inches the galactic past. Secrets that may redefine our place inches the cosmos. In its passage, we find not just a scientific puzzle, but a mirror to our own existence, a testament to the boundless curiosity that drives us to seek meaning inches the infinite. 3i Atlas's journey is one of extremes. Born inches the cold, dark depths of interstellar space. It traversed trillions of kilometers to arrive at our doorstep. Its hyperbolic path, a trajectory so steeply curved that it will escape the sun's gravity entirely, tells a tale of origin far removed from the solar system. Unlike comets born inches the Kuiper belt or Oort cloud, which are bound to the sun's gravitational embrace, 3i Atlas is a true nomad. Its velocity, measured at 58 kilometers per second, is a relic of the gravitational tides of its home system, a velocity that cannot be explained by interactions with our planets. This speed, combined with its trajectory, places its origin inches the direction of Sagittarius, near the Milky Way's galactic center. Here, inches a region dense with ancient stars. 3i Atlas likely formed billions of years ago. Perhaps inches a protoplanetary disk now long since dissolved. The discovery of 3i Atlas was a triumph of modern astronomy. Detected at 4.5 astronomical units from the Sun, it was first spotted by the Atlas telescope, a sentinel designed to warn of potential Earth impacts. Yet its path quickly revealed its interstellar nature. Follow-up observations by the Zwicky Transient Facility and the Very Large Telescope refined its orbit, confirming that it would never come closer than 1.8 AU to Earth. While this ruled out danger, it raised deeper questions. What kind of world could birth such an object? How does it differ from comets shaped by the solar system's history? The answers lie inches its chemistry. Spectroscopic analyses by the James Webb Space Telescope revealed a peculiar mix of carbon dioxide, water ice, and trace gases like cyanide and nickel vapor. These signatures suggest a formation environment distinct from our own, perhaps inches a system where volatile rich materials survived longer under different conditions. Yet 3i Atlas is not merely a scientific specimen. Its journey is a mirror to our own. Like the comet, humanity is a traveler, drifting through the cosmos, seeking understanding inches the void. Our telescopes, like the Atlas and Hubble, are instruments of exploration, tools that extend our senses across the abyss. The collaborative effort to track 3i Atlas from the initial discovery by a single telescope to the global network of observatories reflects the unity of human endeavor. In studying this comet, we do not simply catalog data, we participate inches a dialogue with the universe itself, a dialogue that spans eons and light years. To grasp the significance of 3i Atlas is to confront the staggering scale of cosmic time. With an estimated age between 7.6 and 14 billion years, this comet predates the solar system by over 3 billion years. It is a fossil of the early Milky Way, a remnant of an era when the galaxy was young and turbulent. The thick disk from which it originates, a region populated by ancient stars with low metallicity, holds clues to the formation of galaxies themselves. Stars inches this population, unlike our sun, formed inches a universe with fewer heavy elements, a time when supernovae had yet to enrich the interstellar medium. If 3I Atlas indeed hails from this epoch, its composition could offer insights into the primordial building blocks of planetary systems. But what does it mean to encounter an object so ancient? For scientists, it is a window into the past, a chance to test theories about the evolution of comets and the conditions of the early universe. For philosophers and dreamers, it is a humbling reminder of our transient existence. The solar system is but a flicker, inches the galactic timeline. A brief interlude inches the life of a cosmos that has already witnessed the rise and fall of countless civilizations, stars and worlds. And yet, here we are, capable of detecting a speck of ice and dust that has traveled for eons, capable of unraveling its secrets with the precision of modern technology. The implications stretch beyond science. 3I Atlas forces us to reconsider our cosmic neighborhood. If interstellar objects like this are common, then the universe is not a sterile expanse, but a dynamic exchange of matter and energy. Comets may not be rare outliers, but part of a grander cycle, a cosmic recycling process that connects stars and planets across galaxies. Could life's ingredients, organic molecules, water, and even the seeds of biology have been delivered to Earth by such visitors? The possibility is tantalizing, a hypothesis that bridges the gap between the abstract and the tangible, the infinitesimal and the infinite. Moreover, 3I Atlas's southern origin challenges assumptions about the distribution of interstellar objects. Previous discoveries like Oumuamua and Borisov came from the solar apex, the direction of the sun's motion through the galaxy. 3I Atlas, however, arrives from the opposite quadrant, a region historically harder to observe due to the glare of the galactic center. Its detection suggests that our telescopes may be missing many such objects, that the universe is teeming with travelers whose paths we have yet to chart. This realization is both daunting and exhilarating. We are blind to much of the cosmos, yet each new discovery expands our vision, revealing a universe richer and stranger than we imagined. As 3I Atlas continues its flight, its story becomes ours. From the moment of its discovery to its final apparition, inches the night sky. It serves as a bridge between the known and the unknown, the familiar and the alien. By October 2025, the comet will reach perihelion at 1.36 AU from the Sun, a distance that places it between Earth and Mars. Though it will not be visible to the naked eye, its journey will be chronicled by orbiters around Mars, which may capture images of its coma and tail. These observations will add to the growing archive of interstellar visitors, a dataset that will shape our understanding of the cosmos for generations. Yet even as 3I Atlas fades from view, its legacy endures. It is a symbol of the universe's indifference to our concerns, yet a beacon for our curiosity. Its passage reminds us that we are not alone, inches the dark, that the same forces that sculpted the solar system, the same stardust that forged the elements inches our bodies, are at work across the galaxy. The carbon inches our DNA, the oxygen we breathe, the iron inches our blood. All were born inches the furnaces of dying stars, scattered by explosions that lit up the void. We are the children of the cosmos, and inches gazing at 3I Atlas, we see a reflection of ourselves, transient, fragile, yet endlessly driven to seek meaning. Inches the infinite. As the comet retreats into the abyss, it leaves behind a question that echoes through the ages. What else waits beyond the edge of our vision? The answer, perhaps, lies inches the next discovery, the next fleeting guest from the stars. Until then, we remain stargazers, bound to the earth yet yearning for the heavens. Our hearts alight with the same fire that burns inches the heart of every atom.